signatures. Okay, may I have your attention? So let's get started. Welcome. It is my great pleasure, along with my co-chairs, Shireen and Ron, to welcome you to Salt Lake City for the 8th edition of Medical Imaging with Deep Learning this year. So we have 280 attendees this year from institutions coming across the globe, 24 countries and 4 continents. Thank you all for being here. I want to especially thank those of you coming from overseas for being here and for your continued support of MIDL. We couldn't have made this conference a success without your continued support, so thank you. I also want to thank Infusion for their generous gold sponsorship of this conference. They have a booth they are setting up outside this room next to the registration desk. Please make sure to visit them. I'm sure they'll be happy to show you demos of their work. I also want to thank other sponsors, NVIDIA, Arup Laboratories, the Huntsman Cancer Institute, and Voxel 51 for sponsoring this conference. This year, the conference, MIDL, is hosted by the Scientific Computing and Imaging Institute at the University of Utah, and this has helped us immensely in putting together a cost-effective program. Brenda, Kate, Deb, and Ed have been working tirelessly over the last several weeks to put together all aspects of this, from the housing to catering to registration and live streaming, so thank you. And I also want to thank Paul and Nathan for their help with the multimedia content. I want to thank our volunteers, PhD students here at the University of Utah. We have 20 guys. You'll see them in their orange shirts going around. They're ready to help you with any of your questions. Don't hesitate to approach them. I also especially want to thank Tushar for leading and organizing the volunteering effort, so thank you. This year's program committee consists of Dr. Ron Summers, Dr. Lisa Ko, Dr. Chen Chen, and Dr. Yan Xuan, and they've worked hard to put together a high-quality program. And now I want to just call Ron here to say a few words.
Thanks, everybody. It's a great pleasure to be here and in this beautiful city. I'd like to thank all the area chairs. There were 42 area chairs. Their names are listed here. They worked tirelessly to make sure that all the meta reviews and reviews were all done on time. Here are the statistics on the regular full-length papers. There were 195 submissions, of which 167 underwent review after desk rejections. There were 32 accepted orals for an acceptance rate of 16.4%. The overall acceptance rate was 55.9%. That was 105 papers. There were 42 area chairs, and 220 reviewers completed at least one review. 544 reviews were submitted, and all papers received at least 3 reviews. The program committee would especially like to thank the emergency reviewers who made this possible. Some of them received a request to do a review and had to return that review the same day. So thank you to those of you who helped with that particular effort. For the short papers, there were 125 valid submissions, of which 118 underwent review. There were 87 accepted short papers. The reviewing process consisted of a light review by the area chairs and then the PCs, and for that function there were 34 area chair reviewers.
Thank you, Ron. So this year's program, we have 7 oral sessions, 6 from the conference papers, and also 1 journal to conference track oral session, Melba session. All the oral talks and the keynote talks will be taking place in this room here, Douglas Ballroom, and each oral presentation is 15 minutes in total, 12 minutes and 2 to 3 minutes of questions. If you are a presenter, please make sure your slides are uploaded to the Google Drive link that you should have, preferably the evening before your talk, but let us know if you update it after that. The poster sessions are going to be across just the courtyard here in the Granite Ballroom. So we have 6 poster sessions across the 3 days. We ask that you put up your posters in the morning at your assigned spot, and then the posters will be staying up the whole day. We do ask that at least one author is there to present during the session your poster is assigned to. And also please remember to take your posters down by 5:30 p.m. that day to make room for the posters of the next day. Otherwise, our volunteers will be taking them down and you can collect them at the registration desk. This year's program also has 4 exciting keynote talks. Today, Dr. Tal Arbel will be giving the opening keynote, and tomorrow we'll have Dr. Ruckert, followed by Dr. Rusu and Dr. Alward on Friday. So we're looking forward to hearing their exciting talks. Your conference registration includes breakfast and lunch every day, and as you saw, that's going to be out there just at the entrance to this room. We will also have the coffee breaks, the morning and afternoon coffee breaks out there. Tonight, we'll have a welcome reception also in this room, starting at 6:30 p.m. We ask that you wear your badges, and also importantly, if you want to enjoy alcoholic beverages, make sure to have your ID with you, like a passport or a U.S. driver's license. Utah liquor laws are pretty strict. So tomorrow, we're going to have a gala dinner at the Natural History Museum of Utah, and we're going to have campus shuttles take you up from here to the Natural History Museum of Utah, and then after the event, they'll be taking you back here as well as the Callard Village if you are staying over there. If you happen to have a car, there's also parking up there, so you're welcome to drive up there. Again, wear your badge and bring your IDs, please. So the program already started yesterday with the Doctoral Symposium Day. There were 71 invited PhD students, soon to graduate and already graduated students, and they had, I hope, a great day. Professor Ed DeBella from the Department of Radiology here at the University of Utah gave a keynote. There were academic and industry panels, and the MIDL Young Research Board gave a presentation, followed by a career fair, networking, and some fun at the game zone, and finally concluding with dinner. So I want to thank Ricardo and Shika for putting together this great event. And I also want to take this opportunity to thank Bennett, Dr. Bennett Lenman, for organizing the workshop day, which is going to take place on Saturday after the conference is over. So Bennett, if you want to come up and say a couple of words about that.
Great, thank you so much, Tolga. If you have a little orange sticker on your badge, you've said you are coming to the workshop. If you are around for Saturday, and you would like to come to the workshop, I think we'll have a little extra space. It'll be great. This year is going to be led by Voxel 51. They are an open source hybrid model company where they're really wanting to get dynamically labeling data and algorithms into an open source platform. They're here to help. They'll support transition papers. They've been reviewing many of the papers that are on our MIDL program to see who wants to get their already open source programs into a larger audience. So it's continuing the tradition of MIDL of having industry community coming on in. It should be a lot of fun. It'll be hands-on. It's not in this room. It's on the program committee of where you go.
Yes,
Fair?
thank you for pointing
And
that out.
it's going to be led by Daniel Gural coming up from Voxel 51, and their developers will also be online to help us out. So thank you very much. It'll be a great time. And thank you, Tolga, for letting us have it do it.
Thanks, Bennett. So next, I want to invite Alessa Herring from the MIDL board to say a few words.
Thanks, Tolga. Also on behalf of the MIDL board, welcome here in Salt Lake City to this year's MIDL conference. And of course, also thanks to the organizers that you welcome us here and for organizing the conference. And as you see, there is not only the organizers of every year that plan the conference, but we also have on top the MIDL Foundation and then the MIDL board to give a bit continuity over the years. And this is our current board. If you have any questions or would like to talk to us about something, please reach out. Quite some of us are here this year. But of course, people will leave also the board, and that's always a sad moment, but of course also a moment where we would like to thank people. So Ivana and Bram will leave this year the board, And they have started the conference in 2018 because they thought it's a good idea to have a specific conference for medical imaging with deep learning. And they came up with that idea and just made a conference. And thanks to them, we are all sitting here today and can enjoy all the scientific talks. So thanks, Brahms, thanks, Ivana, for doing that, for spending all the effort. Unfortunately, they are not here today, but I hope they watch the live stream. So a round of applause for them would be great. Thanks. And since last year, we also have a young researcher board consisting of Josh, Anna, Anwait, and Aisha. Where are you there? Could you quickly stand up? If you have any questions regarding young researcher, please reach out to them. They are there for you. And they already organized a lot of great conference or workshops in the last year. For example, the winter workshop on reviewing and writing papers, but also a workshop on medical imaging research in Africa. And it was a huge success so far, so thanks for that. And there are already more events planned, which I'm very excited about. So the next one is about mental health in research. You can register via this QR code, and then looking forward to interactive talk by Sophia Valix. Yeah, I think it will be great. And even cooler, a young researcher showcast, where all young researchers can submit their work, which will be reviewed by the young researcher board. And then you have the possibility to present your work in some oral sessions, online sessions, meaning you can also connect with other researchers throughout the year. And even if you're not able to come to the conference, you can present your work in our community. Then also new this year, we have a special session on the MIDL challenges. And in this session, we will have a presentation about the monkey challenge, which was one of the 3 MIDL challenges this year. Unfortunately, the Puma challenge is not able to attend and will not present, but the Beyond FA challenge will also present in this specific session, but also has a poster on Friday, which you can visit. Then I give back the floor to you, Torga. Thanks.
Thank you, Alessa. Just a few points of logistics before we get started. So there's a Wi-Fi connection. There's 2 networks that are available. The UGuest network is open to anyone, and you can also use the EDU Rome network if your institution subscribes to that. You can use this QR code to get more information. I don't think this needs a reminder if you were here yesterday, but it's hot outside and dry. So you're also at close to 1,500 meters. The sun is strong. Please stay hydrated, drink water. There's water filling stations around. If you're outside for any prolonged amount of time, then I would recommend using sun protection as well. A few locations over the campus of University of Utah that the conference is taking place. So in the middle, we have the guest house and the conference center where we are now. Short walking distance is the Collard Village, for those of you staying there just across the bridge. The Natural History Museum of Utah is up in the foothills. And down here towards the left is the Gardner Commons, where we're going to have the workshop day on Saturday. I also wanted to point out, if you're looking for food beyond the conference, you can check out the area down by President's Circle, around 1300 East and between 1 and 200 South. You can reach all of these locations using the free University of Utah campus shuttles. So the orange circulator, red and Sunnyside routes serve the conference venue. You can use the QR code again here to get access to download this Live Tracker app on your phone to figure out where the shuttles are on campus. And just look for the UU sign where the shuttle bus stops are. If you want to go beyond the campus, then you can use the Utah Transit Authority, the bus system. So there is a WhatsApp group for on-site attendees to communicate with each other if you're interested in joining that. The QR code is here. Also should be at the registration desk. You can scan that to join and chat with the fellow attendees. The website for this year has lots of useful information, including the program at a glance, the more detailed scientific program, locations of venues, and other things. So again, the QR code on the upper right will take you to the conference webpage where you can get all that information. Okay, so without further ado, we're ready to get started in a few minutes with today's schedule. And the first oral session is on segmentation. So if you are one of the speakers in this session, please come up to the front, and we will plan to get started in just a little bit in about, I guess, 10 minutes from now at 9 a.m. So thank you very much. Welcome again. Looking forward to the conference. Yes, yes. So and that's cool. So I had just to help you guys out, present your names. Present your names? Yeah, I thought I have it. I mean, I looked at it. I didn't see what I just looked up. We can check it out over there. We will see the setup.
Oh, okay, perfect. Thank you.
Are you one of the speakers?
Tomorrow, but I haven't printed out just in case, but I wasn't sure what the setup would be.
Yeah.
Thank you.
Hi. Can you also tell us how to pronounce your name?
Rain is like the weather. Rain.
Raining.
Yeah, rain. Yeah. D. How do you pronounce it? D. Yeah. Yes, rain. Perfect. Thanks so much.
That I don't know because we're not handling that.
Okay.
But good to see you. That's fine. Just remind me how do I pronounce your full name?
Spanish name. Sorry about that. That's certainly.
That's okay. It's just so David.
Say it. Thank you.
Two speakers. We have a paper number 2. Yes. Yeah, you can go take a look. It's presenter mode. But before you disappear, I still have a question for you. So, you guys will introduce yourselves. How do you pronounce it? Come closer so that I can. from Fraunhofer Mewis in Bremen, northern Germany.
We have a very exciting program of 5 scientific talks lined up for you. As a brief reminder for our speakers, we have 12 minutes for the talk, 2 minutes for questions. For questions, we have microphones in the alleys. There's one over there, and then perhaps one there. If not, I will walk up and bring this microphone to you. So if you have questions come up, the timeline is relatively short, just 2 minutes. So if we can be organized, that would be phenomenal, so that we have a great discussion on the scientific program. And without further ado, we'll invite the first speaker to the stage.
Yeah, the first speaker and first author of the first paper is Reining Deng from Cornell, collaborating with Vanderbilt. And the topic is consensus-aware self-corrective learning for cell segmentation with noisy labels. So the stage is yours.
Thank you for the introduction. And hello, everyone. My name is Reining. I recently graduated from Vanderbilt University, and currently I'm working with Weill Cornell Medicine. Yeah, it's a great honor to be a first speaker to start up our MIDL conference, and I guess it's just like we submit paper early according to the paper ID. So, but I hope our research can become the stepping stone to inspire the very interesting discussions during the whole meeting. So today I would like to introduce one of our projects called Consensus-Aware Self-Corrective Learning for Cell Segmentation with Noise Labels. The reasons we try to do cell segmentations for renal pathology is that accurate cell quantification can help pathologists in diagnosis. For example, between the normal sample and the disease sample of glomeruli, the density between different cell types are different. So if we can achieve a good quantification of these cell types, we can provide the biomarker for diagnosis. However, if we annotate those images, it's very hard. There's several examples between the disease glomeruli and the normal glomeruli. So based on these images, the pathologist has to annotate cell type, but it is very hard for us to recognize where is the cells and what's the contour of the cells. Even though for the decades of medical training, the expert is hard to find it because the morphology of the cells is very varied due to the staining and the lesions. Luckily, there's another modality of images called immunofluorescence data, try to highlight the protein expressions inside of the cells. So those immunofluorescence data can represent as the stable biomarker to analyze the cell type. For example, if we do co-registration between pathological images and immunofluorescence data, the red signal can represent the podocyte, and then green signal can represent the mesangial. So with this guidance, we can make a good annotation accuracies for our data. So if we want to train a model, we need a large scale of data to get a better performance. However, for the natural images, we are very easy to find lay annotators try to help us to build data sets. However, for our medical images, it's very hard. We need to ask the expert for help to build our data sets. If we compare the difference between two, first, the cost is a totally different story, and then the time cost is very different as well. So what if we provide those immunofluorescence images to the lay annotator, and then we can generate a large scale of data sets with loss cost, and then we can liberate our clinicians to working on their clinical research. That's the ideal solution. So previously, we tried to invite the lay annotator to help us to build these cell segmentation data sets by using those immunofluorescence data. And it's turned out that those lay annotation accuracies is better than the pathologists that only annotate them on the pathological data without any of the immunofluorescence data. So, however, even though the immunofluorescence data can help us annotate the cell types better, it still cannot achieve the 100% accuracy. Like if we calculate the F1 score, it's only around 0.85. So due to the staining qualities, variation between different annotator, and the vision limitation on cell morphology. If we directly input those of labels inside of the model training, we will receive the performance drop from the model. That's why we try to think about how can we recognize the noise from the labels and then improve the cell segmentation performance. Because when humans read the images, we cannot see a subtle difference or like subtle morphologies from images. However, when model reads it, it can recognize the subtle variations and provide the pixel level differences. For example, the model can tell us what's the difference between intensity 48 and intensity 40, but a human might not achieve that. So assumption is that if we let the model to read those images, and the model can give us the better cell representation at the feature level. Therefore, we want to use the model to help us recognize the noise from the labels. So we input images and the annotation to the model, and on the feature map, we try to highlight the region that the model believes it is cells, and also highlight the region that model believes it might be the noise from the label. And then we try to eliminate those noise during the model training. And in this case, we mainly focus on the instant-wise location error, which is false positive and false negative cells are introduced by the late annotators. So before we introduce our method, we define the consensus matrix to tell us the different region between cells and noise. So between the prediction from the model and the late annotations, if both model and the human believe it is cells, or model and model believe it is non-cells, it is called consensus region, then we emphasize all of the information from those regions. On the contrary, if either model believe it is cells, but the lay annotator doesn't believe it is cells, or the model believe it is non-cell, but annotator annotate those regions, we call it disagreement region. And then we wish our model can distinguish real cells and the noise. So this is the consensus matrix. So building on this consensus matrix, we provide our self-corrective learning over methods. So we will dive into step by step. So first, from the output of the model, we calculate the overlap between the late annotation and the prediction from the model to generate the consensus positive region. And then we've tracking back on the feature map and then summarize them into a one-dimension vector, and we call it cell feature. So we believe this feature can represent as the cells, like cells morphologies. On the contrary, we also calculate the disagreement regions between the human and the model, and then we also capture all of the feature vectors from the feature map. And then those feature vectors can be represent both cells and noise because this is a disagreement region. So how can we achieve the noise feature? So we calculate the cells feature with those noise regions features candidates because the assumption is that we believe the noise should be dissimilar to cells. So we calculate the similarity score from those vector candidates as well as the cells feature, and then those weights can represent that whether this vector is more likely to the cells or whether this vector is more likely to the noise. And then we use those weights to sum up the vector from those candidates and then into a one-dimensional vector, and then we call it noise feature. After we receive the cells feature and the noise feature, we also calculate the feature like similarity score heat map from between those feature and the feature map. And then those feature map can highlight the region that the AI model believe it is the cells region or it is the noise region. And then we use those heat map as well as late annotations into the supervision and then to highlight the knowledge from the true cells region. That is the pixel level cells corrective supervision in our design. At the same time, we also want to emphasize the differences between cells and noise at feature level. So we also generate a contrastive learning between cells feature and a noise feature, try to dissimilar the cells feature and noise feature as much as possible. So to evaluate the performance, we first test this on our real data sets, which is we register immunofluorescence data on the histopathology data, and then we let late annotator annotate it and calculate the accuracy. And also try to further test our performance. We also generate two types of the data sets, which is we randomly capture the nuclei region on the images and then add those nuclei into our data, represent as the false positive noise in the data set. And also, we also randomly delete some of the label from ground truth to represent the false negative noise to the data set. So we have one real data set and two generative data sets. So this is the accuracy, annotation accuracy for different data sets. And then we evaluate our performance based on segmentation performance and detection performance. So first, we try to do hyperparameter tuning on the backbone and different hyperparameters, and those results can serve as upper bound for this task. And then for the quantitative results, our model can improve the cell segmentation performance compared to the other corrective learning methods. And those results is try to approaching the upper bound by training without any of noise. And this is a qualitative result. Our methods can achieve the better segmentation performance with less false positive and false negative compared with supervised paradigm. And also the assumption from our model is that our model can reduce the false positive and the false negative region during the model training. So we also calculate the IOU between false positive, false negative region, as well as true positive region. And the results show that our model can decrease the IOU from those error regions. So the reasons we love the MIDL community is that the review process is very supportive. So we receive a lot of good suggestion and comment during the review process. So based on their review, and we think it is very nice to extend the current stage of the research into the future work. So first things is that right now we only analyze the instant-based error, and there's another different noise type such as control-based noise we can explore. And also there's a lot of different methods that we can try. And in the end, it is possible to generate a fully automatic pipeline, directly capture the signal from immunofluorescence data, and achieve the cell segmentations without any human error. So to sum up our work, we propose a consensus-aware self-corrective learning, try to address the noise in the label, and then we test our data in reasoning guide noise generations data, and eventually by integrate the consensus matrix as well as the corrective learning, our model try to address the false positive and false negative error in the data set to improve the cell segmentation performance. And in the end, I would like to appreciate a lot of support from both of Vanderbilt University and Cornell University. And thank you so much for listening. I'm happy to address all of the questions. Thank you.
Yeah, thanks, Reining, for the great talk. Are there questions from the audience, please?
Hello, thank you for your presentation. I have 3 questions. The first one, are the IF images and PAS staining or serial sections or on the same slide?
They are on the same slide.
On the same
They scan the PNS and wash it and get immunofluorescence data.
Okay.
Yeah.
The other one, did you consider to look at the variability between different staining? Different machines, different sites?
Yeah, that's a good question. So currently we only use one machine, from the medical center. But if we have data sets across the different institutes, maybe we can explore that. Okay. That's a very good point.
And how big is your data set? How many glomeruli or how many patients samples have you included in your training?
So in the total data sets, we generate 11 whole slide images, and then we capture them to the patches. The patches are around 1,000 for each cell type.
Okay.
Yeah.
Thank you.
Thank you.
Yeah, so very nice presentation. I have a question more from the cell biology perspective. So some of these cells have very long processes. You know, they can reach hundreds of microns. So I'm wondering, in your contour-based approach, how are you going to approach, you know, the cell boundaries?
So for here, we just do like semantic segmentation with like binary mask. Actually, we didn't do a lot of like exploration about contour based, like whether this contour align the cells or whether it's not. So that is our next step. And also we need to ask like multiple pathologists to annotate the same images, and then we can get a better contours annotation for that to
Well,
explore those questions.
So I'm a pathologist, and
Yes.
so the problem is we don't really see where the boundaries of the
Yes,
cell, and that's
right.
a huge problem. So I'm wondering how you're planning to solve that problem.
So there's a lot of like good tool, for example, segment anything model. Like they can help us to generate the very stable annotation without any human bias. So one of the solutions we are thinking about is that maybe we need like human and a model together. First, human can tell us the location of the cells, and the model can give us more stable because they read the image as the array, like they read the intensity rather than the human, have a human limitation. So maybe those can help us to provide more stable annotation, and then we can interaction between human and model. So thank you.
Yeah, thank you for the great Q&A. And do you want to announce the next talk and I bring up the slides?
Yes. Our second speaker is Mustafir Rahman, who will be talking on a training-free dataset pruning for polyp segmentation via community detection in similarity networks. Please.
Thank you for the introduction. My name is Mustafizur Rahman. I'm a final year PhD candidate at the University of Texas at Austin. In my today's talk, I would like to introduce you with one of our recent method for efficient, data efficient AI. So the titled training-free dataset pruning for polyp segmentation using community detection in similarity network. Let's start with why polyp segmentation matters. Polyp segmentation is one of the critical steps in early diagnosis and removal of polyps that is responsible for colorectal cancer. And the colorectal cancer is the third most common cancer and the second leading cause of cancer-related deaths worldwide. But greater than 90% of the colorectal cancer cases starts with a benign polyps. That means there is no cancer at all at the start, but the malignancy risk can be jumped with the size of the polyp. So if the polyp size increases around 20 millimeter or more than 20 millimeter, the risk of malignancy jumps to around 50%. Therefore, early removal of whole polyp can help in this regard, reducing the risk of colorectal cancer. So polyp segmentation can help in this regard by identifying the polyps early and helping in the removal of the process. However, the polyp segmentation model training and evaluation requires expert annotated datasets, and every model, we need, if it's self-supervised or supervised, we need expert annotation. So expert annotation is a difficult process because we need to first find out the expert trace the polyp on top of the image, and we need another expert at least to confirm the trace like is the correct polyp, and we use that as the ground truth to train our model. So there are several challenges where we are going to annotate a very large number of images, such as we need expertise demand here because experts are usually busy, and we need at least 2 experts, board certified gastroenterologists, to label the polyp images. And in case of that, we have time constraints, because for a single image, we need around 400 seconds to label or make the annotation. However, medical professionals has demanding schedules, and it's very tough to get that time for a very large scale data set. So, and also there are high costs associated with this. So studies show that a single image can take up to $40 US. There is another challenge, that is inter and intra-observer variability, that also increase with the size of data set. If we have more images, there is more chance of this observer variability. This actually raises the question to have a very small or limited data set, but diverse and representative of the whole or large data set. So in this work, our goal is to find or select a limited but diverse and representative data set of the whole very large data sets having very large number of images, but we'd like to have the accuracy that's closer to the original data set, but minimizing the annotation cost and effort. So why does it matter? When we have very large data sets, we have consecutive frames in case of polyp segmentation, but if we have smaller data sets, we can remove the consecutive frames, and we can actually confirm the heterogeneity of the data that can reduce the boundary bias. Another thing, fewer but richer samples can help the expert to annotate it accurately and also reduce the quality control cycle. However, existing data selection methods includes random pruning method. One of the most popular methods, we commonly use random pruning or selection that cannot guarantee the diversity and representativeness. It's usually, it can give us very worst number of samples or good samples. There is no guarantee of this. And there are some works that try to do using science behind this, but that's commonly for classification tasks, and entropy-based methods are common, but that cannot guarantee the representativeness as well. Additionally, to the best of our knowledge, in case of polyp segmentation, there is no data selection or pruning method. So considering all of this together, we introduce a new method so that uses the properties of the images and select a limited, diverse, and represent data sets. We call it prime. So what are the main properties of our prime? So our prime is training free. We do not need to train a model for data selection or annotation. Second, it's completely explainable. So we know why we are selecting an image or why we are removing an image from a data set. What are the steps? So we actually follow two main steps. First step is we construct a network of the images. And second step, we prune that network to find a smaller subset of those images. So here is the network construction process. We consider each image as a node of the graph or network, and then we calculate the pairwise similarity between any pair of images. And this similarity score includes raw pixel intensity based metrics like structural similarity index metrics that can capture the structural similarity in an image required for the segmentation task or purpose. We also tried Pearson correlation coefficient. However, we find out that SIM is performing better here. Afterward, we apply a threshold. So this threshold controls the density of the graph or network. So if we choose a very high threshold, we find a very sparse graph, so less pruning. In case of smaller threshold, we find a denser graph, so more pruning we can done, but in that case, we may lose more accuracy as well. So here is an example graph or network. So we plotted it for Kavasi datasets having 900 images with a SIM similarity threshold of 0.8. So we can find out here that this graph has nodes having connectivity or number of degree more than 100. So that means there are nodes that's similar with other nodes. So using this property, we try to find out a solution to prune this and remove the redundant samples. Those are similar. So we come up with the solution of based on community detection. So we try to detect communities in the networks and select some nodes from the communities and remove other similar nodes from the same community. So we use the Louvain community detection here that detects the community adaptively using modularity-based modeling. So in our case here, for the same network or graph, we have found out that there is 189 communities with a modularity score of 0.51. So that means it has a few very larger communities, maybe having more than 75 images. However, most of the communities are smaller communities with fewer samples. So this heterogeneous community structure helps us to decide which samples to remove and which samples to select from here. So we come up with the solution of selecting top P% of the node from each community. So this top P% based on the node degree. So how they connect to other nodes. And we have found out that this actually gives us a representative sets that's work very well. So in our case, we use top 10% of the nodes. So here is an example from a community. Our prime actually selected this image, and similar images, those are removed from the same community, consist of some of these images. And if you see first image, the left image and the right image, we can see that these two images are very similar, but their manual annotation levels are different in the boundary pixels. So there is boundary bias. So if we can actually remove one of these, our method can help to reduce this boundary bias as well. We conducted experiments on several downstream data sets for segmentation. One include K-basis segmentation. Here we have a plot for different pruning rates that we got using different similarity threshold. And we plotted for different methods, including the random pruning method, the most popular one. And we have found out that our method always topped, like prime with structural similarity index matrix 1. And in case of 56.2% dataset pruning, we can see that our method drops only 0.5% dice score. So the reduction in annotation cost is 56%, but dice score drop it only 0.5%, that's nominal. It also accelerates the training process by 2.3 times. So here is another dataset example. This is a very large scale dataset having 20K images. So in these datasets, we have 4 different test sets. So each test sets, we actually, if we see this, our method prunes 69% of the data and keep only 30% of the data. And our method loses just only 0.6%, 65% dice score. And in case of hard unseen segmentation task, it has just only 0.3% dice score removal. So now I'd like to have key takeaways. So our method cuts the fat and keeps the muscle. That means it removes the redundant images and keeps only the useful images. So there is no training for the data selection. Third, its dataset agnostic, works for a small to large scale dataset. And augmentation helps to boost the performance in our case than if we apply the augmentation pool dataset. In future, we can use other similarity metrics for graph construction. Instead of SIM or PCC, we can use maybe embeddings. And we can use our method in active learning pipeline. So as I close up, so I'd like to let you know that I'm on the academic job market looking for tenure track faculty positions. If you know some opportunities, feel free to keep in touch. Thank you so much for listening.
The paper is open for discussion, please.
Just a quick question. So you mentioned that you build the communities and those you by calculating the similarities between images. So what similarity matrix you use, or does different matrix has any impact to your results?
Yeah. So we actually tested two different metrics here. So one is structural similarity index matrix. So that helps to capture the structural information in an image. So we have found that works better, but we tested also on Pearson correlation coefficient. So that's faster way to actually find the similarity matrix, but it works a bit worse than that. Yeah, it has impact.
We have time for one more short question.
Hi, thank you very much. Very nice work. I have one question regarding the data you use, because usually these images are videos, so you have probably from each polyp a lot of frames. And my question is whether you double-checked whether your method really generalizes across polyps with a similarity, or whether it just clusters all the frames from one polyp together into one node, and then you basically just have one annotation per polyp.
Yeah, that's a great question. So we have actually two different data sets here, like two type of data set. So KVASIR, it's actually heterogeneous data sets. It's not a video data set completely. Okay. So it contains random images there. Yeah. So in that case, it's work. So it confirms that our method is working there as well. So and we also checked it visually, and we found that like in that case, it can actually group different kind of images together.
Yeah, cool. Thank you very much.
Thank you very much. I think there's a lot of opportunity for further discussion on the poster. So let's please thank our speaker one more time.
Okay, thanks. Then we go on to the third speaker in this session, first author of the paper Flare Brain Seg, Fine-Grained Brain Segmentation Using Flare MRI Only, is Edern Lebot from University of Bordeaux.
Yeah, now you're gonna see me fail. Get this in full screen mode.
Thank you very much for this introduction. So I'm going to present the work that we did for MIDL 2025, which is, as you said, Flare Brain Seg, Fine-Grained Segmentation using Flare MRIs only. So there are multiple use cases in neurology in order to do segmentation. You can do the segmentation of lesions, but the case that we're going to focus on today is the segmentation of structures. The idea is that from the brain image, you're going to divide the brain into multiple structures, and you're going to be able to do some sort of volumetry based on the volumes that you extracted from the image. This is really useful in order to do diagnosis, because atrophy is prevalent in multiple kind of disease. And so usually this is done on T1 images. However, it can be the case that in some cases we don't have access to the T1 images. So clinical guidelines, there are rules that clinicians can use in order to decide which image they are going to acquire. And there are multiple cases that started to appear where the T1 image is no longer acquired. It can be the case in multiple sclerosis, where they find that if they can't do the acquisition of the contrast and T1 image, they don't do the acquisition at all. Or it can also be the case in stroke, where there is an issue with time constraints, where they have to do the processing of the subject really quickly. So in the case that the T1 is omitted, in that case, we are not able to apply the methods that we have on the T1 image in order to extract the volumetry. And our goal today was to try to see if we are able to do some kind of method in order to do the extraction of the volumes. This is the problem statement for today. How can we obtain fast and accurate fine-grained segmentation just using the Flare MRIs? So just as a disclaimer, there are actually good methods that you can use in order to do this. And we're going to compare ourselves to this kind of method, which are modality agnostic methods. So are methods that try to segment any kind of modalities. And here, in the methods that I'm going to just show rapidly, in SynSeg, what you're going to do is you're just going to use segmentation maps in order to generate training examples that you can use in order to do the training. So the idea is that for each structure, you're going to sample randomly the intensities, and this way you can show white matters that would have different contrasts. So it would appear as gray or darker, depending on the intensities that was sampled. And you're able to train a model in order to reproduce the segmentation that you had initially in order to do the training. This is really interesting methods, but we're going to compare ourselves to this kind of method today. The method that we wanted to use is to use direct supervised learning in order to reproduce the segmentation that we could obtain from the T1 images. So the idea is to apply a method that works on T1 images. So you have a pair of images, a flare image and a T1. You're going to do the segmentation from the T1 image, and then you're going to train a second model in order to reproduce the segmentation that you obtain just using the flare images. And this is a goal that we want to do today. So we have 3 contributions. I'm going to show how you can construct the training dataset. I'm going to show how we can unhost the dataset in order to ensure the training stability by introducing control quality step and show how the method can be resilient to the presence of lesions. This is the process that we have for you today. So I'm going to go left to right and present to you how we do the processing of the images. So first you have a T1 image and a flare image. And you're going to do the pre-processing where you do the normalization, you remove the bias field, and you're going to do the denoising. And we're going to process the image in two different parts. First, we're going to use a flare image, actually. We're going to use a flare image in order to do the segmentation of the white matter lesions. And I'm going to explain why later. And second, we're going to use a T1 image in order to produce the segmentation that we want. However, it can be the case that in the presence of white matter lesions, then the lesions will appear dark on the T1 image, and usually this means that the segmentation method will fail, and it will segment the lesions as ventricles. This is not what we want. Since the T1 segmentation method does not really work on non-clinically normal images. So in order to account for this, we propose to introduce inpainting. So what we do, we use the mask that we segmented from the flare image in order to do the inpainting in the T1 image. And this way we can produce an image that we can use in order to do the segmentation. And this is a way that you can create pairs of training examples using T1 image and flare images. However, it can be the case that when you apply this process, you can have issues which will arise during the pre-processing step. For example, here I show an example where the flare image was misaligned and the registration did not go properly. So in that case, you cannot use the segmentation as a target because it will not be oriented in the same way and it's going to disturb the training. So you need to account for this. So the method that we proposed for this was to introduce the generation of synthetic training images. So the image that we're going to generate is generated from the segmentation. And for each label, we're going to just replace it by the intensity that you expect for these structures. And this is what we try to do. And we can compute a correlation metric, and in order this gives us an idea of the alignment between the segmentation and the flare image that we have. This is what we do. We compute the correlation similarity metric, so we use a correlation. And we decided to set a threshold, so to reject the samples that we find are misaligned. We decided to fit a GMM component, 2-component GMM model, and we just set the threshold based on the lower end component in order to make sure that we exclude the models that would have lower scores and should be misaligned. This allows us to remove the training examples that are misaligned, and we can use then the example in training. I'm going to talk a little bit about the experimental process. So we used NNUNet for this. The idea was not that it might be the strongest model, but the idea is that it's the most reproducible one. So it's a really popular method that is used by a lot of people nowadays. So this was what we tried to do. And for the training that we did, so we used the data that come from the offset dataset. The offset is a dataset that contains patients with multiple sclerosis, and it's acquired with multiple scanners and multiple sites in France. So we're going to use this as training with additional images that we can use in testing. And we also evaluated the model on UK Biobank, which is another dataset that contains only clinically normal patients. And we're going to compare a method, as I told you, to SynSeg, which is a method I introduced in the very beginning. So we retrain the model to use the same segmentation protocol so that we can obtain a fine-grained segmentation using the synseg based on the segmentation that we generated from the C1 segmentation model. So, and we evaluate the model using the dice and the surface distance metrics. I'm just going to show the result from the dice today. So here we have the table results. So you can see that we get better result with flare balancing. We can have a better idea of the result by just looking at the distribution by structure groups. So what we do is we just average out the results based on the groups of structure depending on the structures that we have. So for example, the white matter, we group the left and right hemisphere. And with this way, we can look at the distribution of the segmentation of the results that we have. But what's more interesting to me is the qualitative results. So we're going to look at the results on in-domain image and on out-of-domain image. Here we first look at the consequence of the synseg training on the outputs that we can have. So on synseg, you're going to see that the white matter lesions are going to be misrepresented as ventricles. And it's not the case for the training that we did using the direct learning process. So on the out-of-domain image, we can look at the segmentation errors that we have. So we can see that synseg mostly have errors with the boundaries of the structures. And we can see overall that flare balancing shows less segmentation errors compared to the ground truth. And this was my presentation for today, where we introduced the three ideas that I talked to you about. So first, we introduced a methodology in order to construct the training dataset using pairs of T1 images and flare images. And then we introduced a quality control method in order to ensure that the training is stable and that there are no misaligned examples in training. And we showed the robustness of our approach to the presence of multiple sclerosis lesions. So the take-home message is that maybe it's good to use modality-specific models. Modality-agnostic models are obviously very good in case you don't know what image you're going to process. But if you know, it might be better to directly train the model. And if you have any question, I'm happy to answer anything.
Yeah, thanks a lot for this nice talk. We have plenty of time for questions. Are there any questions from the audience? If there are none yet, I can start maybe, and you can come up to the mic if you have a question. So you measured the similarity of for the quality control between the synthetic flare image and the actual flare image to check for misalignment. Did you also consider using this correlation measure to for a registration to align the images instead of discarding misaligned images?
It could have been the case. I think it's a good idea, but we did not experiment with it. But yeah, you could just adjust the parameters of the registration if you find that the examples are misaligned. It's a really, really good idea, I think. But we did not try anything like this.
Thank you, very interesting work and well presented. One question that I have is, if you're considering lesions, and I think one of the motivating examples also was stroke, where you might have time constraints, I'm wondering whether segmentation accuracy is really the metric that you care about, or if you should be looking at different types of evaluation to make sure that your image processing is still adequate for the task that you're trying to solve.
I'm not sure I understand the question. If you can repeat.
So, for example, if you have a certain dice score, I think the question is it detection versus is it a segmentation problem, right? So you can have a reasonably low segmentation accuracy, but you still detect it, which is maybe important. In other cases, you might say, I also need to very, very precisely segment. So I wonder whether for the topics that you have chosen, the dice score is the most adequate metric to report in order to...
The case is that we're not looking actually at the presence of lesions. What we're trying to do is to segment the structures. This is because we want to look at atrophy, And in many diseases, atrophy is just a corollary to actually doing the diagnosis. So, for example, if you just do a segmentation of the multiple sclerosis lesion, it's interesting to also find atrophies in the brain in order to do the diagnosis, in order to complete the analysis. The presence of lesions was not included in this work. It's actually future works. I'm working on it right now to additionally output the lesion maps and have a pipeline that segments everything. But the goal is just to segment the structures. This would be my answer.
Okay, then maybe one final question. You were dealing with multiple sclerosis images, and I wonder if there are other pathologies for which you could imagine that this method works well, or if there are also maybe pathologies for which you imagine that this method does not work well, and also where maybe flare images or other sequences could be preferable to T1.
I don't have other example of clinical guidelines where flare is the only modality that is required. This is the intended use case, to be able to do a segmentation when you don't have the T1 image. Because otherwise you can just use a T1 segmentation method, and in that case you would have to do the comparison with the different modalities. Or you just use a multimodal method and you will maybe get better results. Yeah. Does this answer the question?
Yeah, I think that answers the question. Thank you. Then let's thank the speaker again.
If you have further questions, there is a poster as well, so you can come.
Great. The fourth speaker in this session is David Anglada-Roger, who is has titled his paper in a way that makes me very concerned about our biological setup, because two heads are enough, so we better figure out how we grow another one.
Thank you very much for the nice introduction. So thank you everyone for being here. My name is David Anglada-Roger, and I'm a PhD student in the Universitat Politècnica de Catalunya in Barcelona, Spain. I am so glad to present here how we can grow a second head. But yeah, our architecture named Dual Unit for Nuclei instance segmentation. So it's going to be a really short talk. Do not miss the full paper for all the details, and also the code is available and some checkpoints are available if you try out our method, and if you are curious about me, so you can check my LinkedIn page. So I hope some of you know what the whole slide image is. In case you don't, is this kind of images resulting from the scanning process of a stained tissue that is used for the pathologist to diagnose some disease, mainly, for example, cancer. The thing is that these images are so huge that most of the whole slide image processing pipelines, the first thing, or one of the things that need to do, is to crop this image into small pieces named tiled. And in these processing pipelines, there's a small piece which is a tile processing model, which is going to receive these tiles and is going to output some information regarding these tiles. So in this work, we are developing a tile processing model. In this case, we are developing an architecture for Nuclei instance classification. And the thing is that our model is going to receive some tiles and is going to output both the classification for each one of the nuclei in the tile and its segmentation too. So our goal is to deploy this architecture in some hospitals. So we need, obviously, for this architecture to be accurate, but also fast and efficient, otherwise we are not going to be able to deploy. And the thing is, the state-of-the-art models like, for example, HoverNet or CellVIT architectures, in order to solve the problem, they solve 3 different tasks in parallel. The first task that they solve is a binary prediction, where they classify each one of the pixels, either if it belongs to the background or it belongs to a cell. Then they try to estimate the horizontal and vertical gradients in order to find the instances, and when they have found these instances, they can classify each one of the nuclei instances in each one as the available nucleus types. And our observation here, and talking with a lot of pathologists in my project, was that actually the pathologists want this kind of segmentation outputs, but the thing that they're going to use is how many cells of each type are there in the whole slide image in order to extract statistics from that. So our observation is that these architectures are pretty accurate in terms of segmentation, but when you try to deploy them, they are neither fast nor efficient, and that's because in most of that task, the segmentation is mainly used for visualization purposes. So our observation here is that we can simplify this process in order to be able to deploy this kind of architectures. So this is what we propose. This is our architecture. It's a multitask architecture based in the UNet idea, where we have we're going to have an encoder here connected to the decoders with some skip connections. And in this work, for our encoder, well, there's clearly an error here, but this word means encoder. It's a fully convolutional backbone that is going to extract the features, and we test ResNext and ConvNext based encoders. Then we have a first head that is responsible for the semantic segmentation task, where each pixel is classified in each one of the available tasks. And maybe our main contribution is this second head, which is the centroid head. Okay, decoder that regresses a Gaussian density map whose peaks are going to mark the nuclei centroid. And in order to make clear what this head is doing, I prepared a small example here. Imagine that we have these tiles where each one of these white dots represents a centroid of a nuclei. So we built this density map over it that in 3D, I think that it's nicer. So over each one of the nuclei, we built this. Let me go back to see the video. Okay, so over each one of the nuclei, we can build these Gaussians, and the task that this decoder is trying to solve is to regress this Gaussian Gaussian density map. So we have two different outputs for our model, a segmentation map and this predicted Gaussian density map. And what we do to combine them into mimic nuclei instance segmentation is that we're going to find the local maxima of this predicted Gaussian density map, and we're going to use these local maxima as markers over our segmentation map in a watershed-based instance delineation. And the thing is that using this combination of outputs, we can mimic instance segmentation and classification just performing semantic segmentation and a density prediction. So as you can see in this example, if we find a local maxima that falls in the background and is not related to any connected component predicted for the semantic segmentation head, this centroid is going to be discarded. But for example, in this region over here, where we can see two cells that have been predicted as one connected component, due to the use of this density prediction, Gaussian density prediction head, we can be able to detect these both centroids, and this allows us, using a watershed algorithm, to divide this connected component into two cells, which is actually the output that we should expect for these cells. So this is our architecture, and actually this, as you can see, as you are going to see now, is pretty accurate, but also is fast, and it's efficient, so we can deploy it to the hospitals for the pathologists to use. So we train that with using a multitask loss function with two terms related to the semantic segmentation. One, we use the dice term and the cross entropy term, both weighted by using the inversity frequency class weights to balance class representations. And in order to mimic the binary head that, for example, Hovernettle's LVIT had, we apply extra emphasis on the background class in order to improve the cell background separation, and actually result to work really good. And our experiments show that this dice term is more related to the semantic segmentation accuracy, and this cross entropy term is more related to the classification accuracy. And also we have a mean square error term in order to penalize the difference between the predicted Gaussian density map and the ground truth Gaussian density map. So this is our final loss function. So regarding the results, we test this architecture on multiple stains. Obviously, we test it in some well-known data sets as PANUC and CONCEPT, but also we wanted to test it in another stain. We tested in immunohistochemical stain in Ki67 in a private data set from my project. And as you can see here, our approaches are the red one and the purple one. We can accomplish in terms of detection and classification metrics comparable to the state-of-the-art results. And regarding to the segmentation, as you can see, qualitatively speaking, we can see that our proposed segmentation is as good as the available ground truth, and in some cases, we can say that maybe it's better the ground truth, like for example, in this case over here. So the same analysis can be performed in the CONCEPT dataset, where we accomplish, compared to the state-of-the-art results in terms of detection and classification metrics. And if we look at the segmentation output, we can see that is as good as the ground truth, the available ground truth. So it served for visualization purposes, which was our main goal. And regarding another stain, in Ki67 stain, we can see exactly the same results, okay? In some of cases, we accomplish state-of-the-art results, and in terms of segmentation, our segmentations look so pretty good. Okay, but our main contribution here is the efficiency gains in terms of inference time and in terms of computational cost. We compared our architecture in terms of inference times to the hovernet architecture. In total time to process the whole dataset in Concept and Panook, we are able to reduce significantly the inference time needed to process these images, but we also wanted to compare our architecture with the state-of-the-art model in terms of accuracy, which is the CERVLT, and the state-of-the-art model in terms of efficiency, which is the Nuclei model, and we are able to reduce the computational cost, and we are able to reduce the runtime latency of our architecture. So the conclusions of this work is that we get faster inference, but we stay with the same accuracy, that we can sacrifice only minimal segmentation quality in terms of metrics, but the visual results are as good as the available ground truth, and our main contribution here is our efficiency gains in terms of inference time and computational cost. And also in the paper, if you want to check it, we prove that actually this architecture is more robust to stain variations in hematoxylin and eosine, which is actually a really a common problem in this type of models. So I'm really lucky to be able to collaborate with the Digipatix project. So, well, this is Catalonia, a region from Spain. And yeah, actually, the dual unit is going to be deployed in these hospitals in their whole slide image processing pipeline. So with some private optimization code, we are going to be able to process whole slide image and to detect all the nuclei of the tissue of the whole slide image in 3.5 minutes, and we are going to be able to process a lot of whole slide image daily within this project. And just please do not take pictures from that because it's not published yet, but we are working on train time calibration and inference time uncertainty quantification in this architecture, and we accomplish that, which are two main things in this kind of architecture. So this is what I'm working on, so feel free to ask for uncertainty related questions. And before you ask me, yes, we are going to test some transformer-based encoders, and we're going to test some foundational model backbones in order to try to improve the accuracy, but we have to always look for the efficiency cost that these kind of architectures are going to have, so this trade-off is what we want to balance. So again, thank you very much for your attention, and here you have all the information available. Thank you very much.
Thank you, well done. We have time for questions.
Thank you for your nice presentation. So I have a question about the performance.
Excuse me, I cannot hear you, so.
I have a question about the performance of your model on the specifically on tumor cells and macrophages, because you only mentioned about the Ki67,
yes,
which is only for cell proliferation. How about the tumor cells or macrophages? How well your algorithm, your segmentation works on those type of cells?
I don't know, because we haven't tested our architecture on this type of cells. What I can say you is that I think that the Panook, both in which kind of stain are the cells, hematoxylin and eosine?
So you can see them in the even H&E images, the tumor cells and macrophages. So I don't know if you have any pathologies in the room, they can help you more.
No. Obviously, I'm not a pathologist, so I don't actually know what type of cells are you talking about, but what I can say you is that Panook and Concept dataset, especially Panook dataset, it has 19 different types of tissue with different types of cells, so I would say, because I have to say that would say that because it would work, but if it's a task that it is related to cell nuclei instance segmentation and classification, I think that it would work, and we could pre-train with some of these open source data sets, and maybe it could work, but I cannot tell you exactly how it works.
The reason that I'm asking, because you mentioned a lot about the Ki67,
yes,
but the Ki67 only stain one type of cells, just cell proliferation, not the other type of cells. So
yeah, but in Ki67, for example, we had a huge problem, which was detecting the non-epithelial cells, because I work in brain breast cancer. So actually, we had 3 different classes on that data set, which were positive, negative, and non-epithelial cells in order to be able to estimate the Ki-67 index properly. And actually, this architecture was good in both types. First, dividing the cells in epithelial and non-epithelial cells, and then inside the epithelial cells, finding the positive cells and the negative cells in order to perform this Ki-67 index. So we test on that too.
Okay. And the other thing, have you tried to because we have cell pose is very famous in the cell pose segmentation, is very famous in the commercial or in the industry. Have you tried to compare the performance of your model with that?
Actually, that was one of the questions from one of the reviewers. So no, we haven't compared our model to STARDIST, neither STARDIST nor cell pose, because our main metrics here were more related to classification and detection. And I was saying we were just looking at segmentation as a visualization tool that the pathologists asked for that. So no, we didn't compare to that. But as I said to the reviewers, we should have done that, and we are going to do that. So
thank you.
Thank you very much for your question.
Okay, as there are no more questions, this brings us pretty much on time. So let's thank our speaker one more time.
Thank you very much.
Then it's my pleasure to announce the last speaker in this session. Dingje Su is the first author of the work titled Shape-Guided Anatomy Segmentation with Mesh Prompts. And he's from Vanderbilt.
Hello, thanks for the introduction. My name is Dingje Su. Today I'm happy to present our recent work titled Shape-Guided Anatomy Segmentation with Mesh Prompts. So just like the large language models, vision foundation models have gained increasing attention nowadays. And a prominent vision foundation model is called the segment anything model. So this model will take 2 things as input, an input image and a prompt to specify what to segment in the image. The promise of this technique is that it can be used to segment new things without need for retraining. And this is of particular usage in medical field because the data scarcity is a very common issue in the medical field. Therefore, there are many previous studies that have attempted to adapt this framework to use in medical images. And for example, we have the segment anything in medical images, and a lot of other recent and high-quality research work. And because all of this work is based on the original framework of SAM, so they largely rely on 2 forms of prompts, the sparse points and the bounding boxes. In this work, we try to ask one question: are these prompts ideal for anatomy segmentation? And if they are not, what are other possibilities? We first try to point out 2 limitations with these prompts. The first is that they cannot be used to clearly distinguish structures that are separated by implicit boundaries. For example, in the temporal bone CT images, there are 2 structures near the ear called scalar tympani and scalar vestibuli. These 2 structures have different functionalities, but they are not clearly separated in the CT image. Therefore, in this case, it's difficult to use points or bounding box prompts to specify which structure we want to segment. And another issue is that these prompts lack the shape information. It does not constrain the segmentation in terms of the anatomical shape, which is usually a very strong prior in human organs. Observing these two limitations, in this work we try to propose a new segmentation task. That is, we prompt the model with a surface mesh that describes the shape of the anatomical structure, and plus 1 center point to roughly localize the prompted mesh in the test image. The ultimate goal of this project is that after training the model with many organs and on many image modalities, it is able to segment a new structure in a new image modality. However, in this project, we are less ambitious. We do not try to build a foundation model. Instead, we implement an effective framework to solve this proposed task. And we are aimed at to make it able to segment something, if not anything. This is the overall workflow of our framework. So in the beginning, we have a gallery of anatomical meshes. And for each structure, we can have several meshes, and they are selected from random person. And now if we want to segment the liver in a test image, we first choose the liver mesh as the prompt, and then we specify the rough center point in the image to roughly localize the mesh in the image. And then we convert the prompted mesh to a signed distance map. This essentially transforms a set of 3D points into a volume. After that, we can use a registration network to deform, to predict the deformation between the distance map and the CT image. And finally, we can use the deformation field to warp the prompted mesh to fit it in the test image. This framework is agnostic to the choice of registration network. We can use any models. And in this work, we use something called the vector field attention network. And the uniqueness of this method is here. The displacement of every voxel is determined according to its similarity with nearby voxels. This is unlike other techniques such as the voxel morph, where the displacement of the voxels is predicted not directly depending on the voxel similarity, but in an entire black box. To train the network, we need a supervised segmentation loss term. And in this work, we use the hyperbolic transfer distance between the prompted mesh and the mesh after deformation. And this loss term allows us to compare different meshes that have different numbers of points. However, in most data sets, we don't necessarily have the ground truth meshes, and in most cases, we have the binary masks for the structures. And in that case, we can simply convert the binary mask to meshes using the Marching Cube algorithm. And in addition, we need to have a regularization term on the deformation field. We do our experiments on two different data sets. The first is the temporal bone CT images. And this data set is special because for these 4 structures listed here, we have they are segmented using the active shape models, which means that we have the ground truth meshes for them. And not only that, we have the point-to-point correspondence between the ground truth meshes. And using that, we can evaluate the surface correspondence after the segmentation. And the second data set is the body CT images, which is a subset of the total segment data set. We select the subset that fully covers the 4 structures listed here. And for this data set, we don't have the ground truth meshes, and they are converted from the binary masks. To compare our method, we considered 3 baseline methods. The first is MATSAM2. Because our registration network works on 3D volumes, so we consider a 3D variant of the SAM model, and we fine-tune it on our specific data sets, so we make the comparison fair. We also compare to the NNUNet and image registration. For image registration, we use the same vector field attention network to register an atlas image to the test image. And we train it using the DICE plus MSE loss. This is the pretty standard way of using a registration network. We compare to it to show that our new use case does not break it down. Otherwise, it means that the using registration to solve the mesh prompted segmentation might not be a good idea. Here are our results. We call our method MPS-Reg, standing for mesh prompted segmentation using registration. We can see that for both data sets, our method produced very high dice on both data sets. Next, if we compare to the MATSAM2, we can see that the performance is much worse. And the performance for the cochlear data set is particularly worse. That's because the cochlear structures usually have very complex shape, and the implicit boundaries are very prevalent in the city image, making the points prompts less effective. Let's look at one visual example. This is the ground truth segmentation of the cochlear structures. And this is what produced by our proposed MPS reg, which looks very similar to the ground truth. And this is what from the MedSam too. We can see that the segmentation is just not anatomically correct. Next, we can observe the same thing on the body's data set. Now the MedSam2 performs a little bit better, but we can still see that the anatomic structure on the surface of the heart and the liver is not preserved very well. Next, we compare to NAUNet. We see that NAUNet performs very good on the cochlear data set, but much worse on the body data set. The reason is that for a fully supervised method that does not contain any shape constraints, and like NAUNet, the performance highly depends on the data similarity between the test and the training distribution. And because the cochlear structures does not show much variance across different people than the body structure, so the NAUNet can effectively memorize the training set and perform equally well on the test set. But this is much more difficult on the body data set. And finally, we compare to the image reg and image registration, and surprisingly, our proposed method even outperforms the image registration, even if we use the registration network in a very untypical way. And not only that, we have observed some additional advantages of the MPS reg compared to the image registration. The first is that MPS reg can map a point on an anatomical surface more accurately to another surface. And this can be reflected by something called the surface correspondence error, as you can see both from the box plots and the heat map here. The MPS reg produced much lower surface correspondence error than the image registration. And this solely comes from the fact that we are using the chamfer loss instead of the dice loss. The second advantage is that the MPS reg is much more stable when we change different prompts compared to the image registration when we change different atlases. This is because when we change different atlases, both the relative position of the organs and the shape of the organs will change. But when we use the MPS reg, we can individually localize the organ in the test image, so that eliminates a huge source of variance. I want to discuss one limitation with our current work. On the left, you see how the model behaves on the liver and heart. These two structures are included in the training set. So you can see the red region is the ground truth, and the yellow is the starting point, and the blue contour is the end point after deformation. You can see that it performs very well. However, when we test the model on unseen structures, for example, we use the spleen as an additional test structure, then sometimes it still works, as you can see in this case. It kind of learns how to match the edges in the image while maintaining the overall shape. But in most of the cases, it does not work. This is to be expected because we only train the network on 4 to 5 structures with a few hundreds of training examples, which is far fewer than the 11 million training images used by SAM. So to conclude, we implemented a new segmentation task, then we have shown that it works very well for the data sets considered so far. And the limitation includes, first, it may not work very well with a lesion or tumor, which lack shape prior. And secondly, apparently we need much more training to build a really generalizable model. I would like to thank my advisor and all the funding sources and the collaborators, and I would be happy to take any questions.
Yeah, thanks for the very clear talk. We don't have much time for questions, but if there are some from the audience, luckily my main question was already answered during your talk. Good job. So maybe you want to ask one?
So just briefly, and maybe this is more research philosophy than actual approach, is that the way how I understand SAM methods is that they trade off human collaboration for prior knowledge, right? So you can solve problems semantically that are open set because you can introduce human knowledge in order to prompt the model and get the information that you want.
Yeah.
If you already inject a lot of prior information, it seems to me that sometimes the models are a little bit overkill. Now, in your experiments, you're finding good numbers, and you know, if you try hard, you'll find good numbers. I'm just wondering, why do you think that this specific approach, prompting the model with essentially a second alternative segmentation method to begin with, is a good approach forward?
Yeah, thanks for the question. It's a very good one. I think the key limitation with SAM is that it's difficult to use points to specify what to segment in the image. For the natural images, it's less an issue. But in medical images, as we have shown in the city images, sometimes the structures are not clearly separated. So if you points, then you need to add many negative and both positive and negative points. And that is much human burden to do so. And to use the mesh as an additional piece of information as described, it's just to simplify the workflow of the prompting. So we can just use a full specification of what to segment in the image and use that conveniently during the inference time.
Yeah, I think we can conclude the session then. Let's thank the speaker again. And also thanks to the audience for all the great questions. And you want to say something?
Yes, I think the program continues with 15 minutes of coffee break right outside, followed by a poster session. So please join everybody at the posters and have a good session. Thank you. Yeah, of course. Yeah, enjoy the poster session.
Professor Tal Arbel to give the opening keynote today for MIDL 2025. Dr. Arbel is a professor of electrical and computer engineering at McGill University, where she is the director of the Probabilistic Vision Group and Medical Imaging Lab in the Center for Intelligent Machines. She is a Canada CFAR AI Chair and a core member of MILA, the Quebec AI Institute founded by Turing Award recipient Yoshua Bengio. She is a recipient of the 2019 McGill Engineering Christophe Pierre Research Award. Her research focuses on the development of probabilistic causal deep learning methods in computer vision and medical image analysis for a wide range of real-world applications. The machine learning algorithms developed by her team for the detection and segmentation of lesions in brain MRI of patients with multiple sclerosis have been used in the clinical trial analysis of almost all new MS drugs currently used worldwide. She regularly serves on the organizing teams of major international conferences in computer vision and medical image analysis. She was an associate editor for IEEE Transactions on Pattern Analysis and Machine Intelligence and Computer Vision and Image Understanding journals. She is currently the editor-in-chief and co-founder of the archive overlay journal, Machine Learning for Biomedical Imaging, MELBA, associated with this conference. Her keynote today is titled, The Promise of Causal Deep Learning for Personalized Medicine Based on Medical Images Towards Safe and Trustworthy Clinical Deployment. Please join me in welcoming Professor Tal Arbel.
Thank you so much for the kind introduction. I am truly humbled to be speaking to our MIDL community here today, especially at this point in the evolution of AI. By way of a more personalized introduction, this is an MRI scan of my brain. Okay, so today I'm going to start my talk talking about deep learning for personalized medicine, arguably sort of the holy grail for clinical care. I'm going to talk about some recent work that we're doing in this space, both the dream and a lot of the challenges that are still present and that we're working on. So before we go anywhere, let me just explain a little bit in terms of the context. So here's a typical clinical scenario. You have a patient that comes in, let's call him Joe. He has an illness, he's been diagnosed. We have a clinician who would like to treat him, and there are 3 different treatments available for this patient. And they have to decide which is the appropriate treatment for this patient. So the clinical, the typical strategy might be, okay, let's look at the average treatment effect across the population and look at the drug that has the highest efficacy. Okay, so let's say that's the first treatment, but this might not be the best treatment for Joe. So by way of personalization, we often have access to clinical and demographic information about the patient. So treatment decision could then be made, for example, by looking at the conditional average treatment effect, conditioning on the subgroup. So for example, in this case, males of the same age as Joe typically do well in the second treatment. So why don't we try that one? However, this again might not exactly apply to Joe. So again, medical imaging provide a lot of personal information about the patient. So the question that we're asking is, what if we could integrate clinical, demographic, and medical images into an AI system, and we could provide the clinician with some kind of tool that would predict in the future what would be the best treatment for this patient? How will the patient respond to treatment A, B, and C in the future? And then we'll give the patient the specific drug that would be useful for them. Okay, so this is the promise of AI for image-based personalized medicine. However, unfortunately, the promise is not yet met. So why is that? So we're all in this field together, and we know that deep learning has a lot of challenges associated with it. I'll just talk about a few right now. First of all, we know that deep learning has the possibility to make potentially deadly mistakes. So here's a specific example during COVID, and you've seen many examples. And so the idea is that in order for it to be trustworthy, we really do need to convey the degree of confidence in our model's output. Okay, so that's the first thing. Second thing is that we know that deep learning models are black box models, and clinicians will have a lot more trust in the model if we can actually open up the black box, because they would like to know how the AI model actually leads, what led it to make a specific conclusion. And finally, we all know that deep learning model can be biased and unfair. Here's some examples that are well known in the literature that, for example, it may not work very well for certain subgroups. For example, if we're diagnosing skin cancer, we know that it doesn't work as well for people with darker skin. So we need to expose the biases and, in fact, mitigate these biases as they come up. So in this talk, I'm going to talk about some deep learning work, specifically causal inference for personalized medicine from patient images, and I'm going to talk a lot about building trustworthiness and reliability into our models for real-world clinical applications. So many different areas to think about. I'm specifically talking about three, which are a big focus of the field in general: uncertainty estimation, explainability, and improving fairness and biases. And these are three big themes in my lab, with a lot of different work that we're doing on these spaces. Case study will be multiple sclerosis in the first part. I'll talk to you about that. And then we'll move to chest x-rays, and you'll see the different tools that are applicable to different things. Finally, I'm going to end with some new frontiers in modern deep learning, both the promise and the challenges. And we're going to talk a bit about MLLMs and agentic AI. Although I've done quite a bit of work, I'm going to focus a little bit on foundation models for explainability and fairness and biases. Okay, so let's start with multiple sclerosis. Multiple sclerosis is the most common neurological disease affecting young people, and the hallmark of MS are these lesions that appear in brain MRIs. So here you can see each row is a different patient. You have different MRI sequences, and what you're seeing now is the patient images over time. And as it evolves, you can see lesions that are appearing, particularly T2 lesions are bright, and you can see them appearing, resolving, and more appearing over time. So why is this important? So here's a baseline image of a patient and the same patient 2 years later, and you can see the appearance of new and enlarging lesions on successive MRIs across time points. And this is really important. These are markers, MRI markers of new disease activity since the previous scan. Okay, so they're telling you something about the patient's disease activity. For example, the patient is experiencing a relapse. And so there are treatments that exist. The treatments are focused on, or have been focusing on, suppressing new lesion formation. And although they manage symptoms, they don't actually mitigate or stop the long-term disability progression associated with MS. And although there are all these treatments available, they have different efficacies, different costs, different availability, different risk profiles. Unfortunately, there is no cure. In our lab, we have actually what we call big data, which is the largest federated data set of MS patient images acquired during almost all the efficient clinical trials. We have over 10,000 patients so far, and more coming over time. We have images, we have lesion labels, we have clinical and demographic data, patient outcomes, tests, and so on. So what we're going to look at for this example is 4 randomized control trials from those that range from no proven efficacy all the way to high proven efficacy. And the idea is the patient comes in, and this is their brain scan, and the clinician is thinking, okay, what treatment should I use for this specific patient? So I'm sure you're thinking, why don't we just choose the one that's the highest efficacy? Because the highest efficacy, as I hope you've seen, is not always the best treatment for this particular patient. We really need to sort of mitigate and look at efficacy versus, a risk factor and so on. So the idea is also that wouldn't it be nice if we can also predict if there are a number of different treatments that would work well for this patient to show them all to that particular patient so they can make a more informed decision. So we've been working on causal deep learning for image-based personalized medicine. In fact, this first paper was at MIDL 2022. And what we're saying is that, the patient comes in, we have MRI sequences and lesion labels, we have clinical and demographic information. And what we're aiming to do is use deep learning models that can actually predict how the patient will do on all available treatments and on placebo so that we can tailor whatever the model learns to this specific patient. So, the idea would be that during training, you would have only the factual treatment arm that they were on, but during inference, you can actually predict how they would do on all of these arms. And so you can see here the output of the first part is predicted future disease severity. So for example, you would say they would do very well on treatment A, but not so well, for example, on treatment B. And then the last part is we are predicting future disease efficacy. And what that means is how well would this patient actually respond to each of those treatments? And for that, we have to compare to placebo, as we'll show in a second. So let's look at the first part, which is predicting future outcomes on or off treatments. In the context of MS, the first paper that we were looking at was just predicting the number, regressing the number of new and enlarging T2 lesions 1 or 2 years ahead. Okay, so treatment, no proven efficacy, you might have 3, but high efficacy, you might have 0. Okay, so during training, like I said, you train on the factual arm, but during inference, you can actually look at all of the outcomes, factual and counterfactual. So here's an example just showing this a little bit. We have patient A who comes in here. Patient A is factually with the star on placebo arm. Okay, so this patient factually had almost 20 new and enlarging lesions 1 or 2 years later. And in blue, you can see all of the results of inference from new and enlarging, from no proven efficacy here. It's not really working, to high efficacy, okay? And the line there is just an established line for what drug escalation threshold. So basically it's saying if you're in the clinic and you have more than, let's say, 2.5 or 3 new lesions on a drug, we would switch you, okay? So the idea to show you is that you can see how the model is predicting that, in fact, this patient would have 2 different drugs available to them that are under that line. But a different patient comes in and factually they have, let's say, 4 new enlarging lesions will happen, and our model actually says, actually, for all the different drugs, you would be under that threshold. So in fact, you have 4 different possibilities available to you here. So this is just trying to show you the kind of personalization that we're interested in. So the second part is predicting future treatment effects. So if you actually look here, what we have to do is this is the causal effect of treatment on the outcome of a patient. So in the context of new and enlarging lesions, you basically are predicting the future individual response by looking at the difference between the result on the treatment and on placebo, because that's telling you the reduction in the future new lesion count relative to treatment or placebo. So now, okay, great. Are we ready for clinical deployment? Well, not so fast. Let's look at some of the different aspects of trustworthiness which we have to build into our model. And so this is going to be a theme throughout. The first one is uncertainty estimation, which is a big focus in my lab, as was mentioned, probabilistic vision lab. And that's an area that we're focused on quite a bit. And so we know that if we actually say, here is a patient that comes in, our model says, hey, this patient will be a future responder to treatment A. AI can make mistakes, and there's a lot of risk in just providing that to a clinician. So the idea would be, what if we could quantify reliably the degree of confidence we have in our predictions? So this led to another sort of body of work, which is instead of just regressing the counts, we have a probability distribution, which says how we would do, for example, in blue, the distribution over the treatment arm, and in pink, for example, the distribution over placebo. And now we're looking at overlap of probability density functions. And we propagate that to the distribution of individual treatment effects. So therefore, we would have, for example, an entire density function that says something about the probability of response. So why is this important? If you look at 2 different patients, patient A and patient B, you will notice that if you just look at the means of these distribution, that a deterministic prediction of the outcomes and the individual treatment effects is not enough to make clinical decision support effective. Because if you look here, the patients have similar means in all of their distributions, so similar expected distribution, or IT, individual treatment effect in blue, between drug and placebo, but with different levels of confidence. So in fact, we're much more confident in what we're saying for the second patient. And therefore, that second patient might actually be a better candidate for things like trial enrichment, where in trial enrichment, we would see who might be a good responder and then bring in more patients like that. So I want to just harp on that point. If we can get a probability of response, then why is that interesting? Because we have drugs that, what do we mean by no proven efficacy? The drugs have to actually work for most people to be approved. But we know that there are some people that did, in fact, respond to the drug, just not a sufficient number. So this is meant to show you in red is everyone who didn't respond, but we know there's some greens that, in fact, did respond. And in this no proven efficacy, it might be like at 18%. So what we have found is with our model, we can actually find a probability of response that's very high and select those patients that in fact did respond with these high confidence. And why that's important is in low efficacy drugs, that'll allow us to do things like, you know, bring the drug back and show that we actually can find people that, that actually did respond. So this is good for enrichment, but it's also good in terms of, I'm just going to go right here, to the clinical decision support. Because if it can predict, for example, that this patient would be a potential responder to 2 drugs, we actually can look at the probabilities and say, but I'm much more confident in the second one. And then the patients have more options and also better informed decisions in the clinic. Okay, so finally, is the last part that I wanted to mention here is that, you know, we are limited if we're just going to predict one outcome. Okay, we have longitudinal diseases and they require the temporal modeling across all through time for treatment effects. Okay, why is that? The drugs might actually affect the patient differently over time and across the population. So if you actually look at this patient that comes in, for drug 1, you will see that it looks like the patient's doing better, but eventually gets worse. And for drug 2, the patient actually gets worse, but then gets better. Okay, we need to model the entire temporal evolution of the outcomes to be able to predict the entire trajectory of those outcomes over time. And so that's something that we're interested in. Then we would be able to say that actually don't look short term. Eventually, the drug will kick in and drug 2 will be better. So this led to us looking at multiple sclerosis again, where this is a long-term chronic disease. And instead of just looking at lesions, what we were really interested in is going directly to the common clinical endpoint for clinical trials, and that's the EDSS score. It's a disability score from 0 to 10, which tells you how much disability a patient has. And so what we ended up doing is building entire trajectories of disability for each patient. So if we actually look here, these are 2 different patients and at baseline. This is the EDSS trajectory. So in purple, it's treatment A, and in blue are treatment B. These are actual results. So what you can see here is that in both cases, treatment B is preferred. There's a lot of noise in the process. Treatment B might kick in faster, or treatment B might eventually actually reduce things much more. And this is something we need to capture. We need to look at longitudinal diseases and really capture that variability. So without getting too much into the model, we built this probabilistic temporal model to predict treatment effect and uncertainty estimation from 3D MRI. So the input is MRI and anything else we have, the type of disease, the baseline disability scores, anything we have. And during training, we have the treatment, you know, we know the treatment arm that they're on. We actually built the EDSS trajectories in latent space. So imagine like an entire trajectory in latent space. But then during inference, what we can do, which is very cool, is we can have a continuous future trajectory for every treatment, but also we can perform causal inference. This is not working. Causal inference to actually say not just how will it do factually, but counterfactually as well in latent space. And then you can decode this to actually look at the disability scores over time. And you can sample that at any point in a long time. And then the differences become the differences between these two. And the important point is also we estimate the uncertainties along the way. EDSS scores, as many clinical scores, are very noisy, and we do that through a causal neural stochastic differential equations. Okay, so that gives us some element of the stochasticity of it. And you can look up that paper, which is a collaboration with Microsoft Research as well, all of these, their causality group. So one thing just to show you quickly is that our model, these are all the drugs from the trials that we discussed. These are a lot of different trials that we had here. And we have disability, we have normalized EDSS, and all this is showing is the more certain our model is, the lower the disability scores were, the error in the disability scores were. So the factual predictions are in fact working, and their correlated error is related to uncertainty. I won't get into all the details here, but uncertainty, in fact, allowed us to take a drug, in this case natalizumab, and when we actually are very confident that this is a high responder, we actually are, with uncertainty, we're able to discover a subset of patients that would be future responders to the drug, And this provides, a lot of promise for a lot of diseases that have no cure. Okay, that brings us to explainability. All right, so let's move on to explainability for a second. And this is going to be a theme that is very prevalent in our lab. And Amar Kumar, a PhD student in my group, will be speaking a lot more detail about some of these models that I'm presenting. But much more generally, explainability is a theme in our field. And it's also it's been a theme in our lab for a long time now. So the question is, when we say, does this patient have pleural effusion? Here's a chest x-ray of a patient with a disease, and the black box classifier says yes, and our clinician would like to know why. So here's a clinician, and the model then, we have a lot of different tools available to us. Many different people have worked in this space. But if you look at things like GradChem, it actually tells you where the model was looking, but not exactly what it found. It just says, I'm looking generally in the area of the pleural effusion. So we're asking more the question of what are the specific markers for that patient that were indicative of pleural effusion? Again, it's personalized to that patient, not just generally. So here we basically, again, look at causality. This is explainability via counterfactual image generation. So we have the image of when it was sick. What would it look like if it were healthy? And the idea is if we look at the difference, we hope that the difference is really in the area that we care about for that disease. So here we have an image on the left. You can see pleural effusion. That's the area of the disease. We only want changes there. We want to make sure, these are the goals, that we don't have really big changes anywhere else and that we end up with something in the right class. We actually want this to be a realistic depiction, and we want it to be high resolution. So in comes foundation models, vision language foundation models. We know that they've been hugely successful in the field of computer vision. You give it language prompts and it gets very, very beautiful pictures in high resolution. And so we introduced PRISM. Actually, we're introducing PRISM here shortly, as a model that takes the pre-trained image encoder and the clip encoder and fine-tunes it on medical images, in this case chest x-rays. And the first thing we found is that it does make very pretty high-dimensional pictures and really high-resolution pictures that look a lot like patients. Okay, so here we just say chest x-ray of a patient with no known disease. On the left, in the middle, it's pleural effusion and support devices. So the support devices that we have, you can see wires, tubes, pacemakers. This is in the general category of just support devices. And in the yellow area, you can see the area of this pleural effusion, and the arrow shows a support device. And then cardiomegaly, which is an inflammation of the heart. So you can see it, compare it back to no known disease. You can see there's an inflammation in the heart. So the whole point was just, can we actually use this for medical image generation in the context of explainability? So counterfactual image generation. And so this is sort of where our focus has been. And I'll just touch on this because Amar will go deeper into that. But PRISM actually synthesizes images of the size of 512 by 512. We've actually reached much higher resolutions now. And it makes precise changes, edits, in the area of interest. So for example, this is a patient with no disease, and it's male. And we want to change one at a time. What if it had pleural effusion? What if it was a female? And so here's one example of a state-of-the-art model that's based on structural causal model and based on VAEs, not on VLMs. And you can see the top is a change to pleural effusion, and the bottom changes to female. It's not a very high resolution image, and also it changes the image a lot from the patient that we're interested in. So our method actually makes changes in the area of the pleural effusion at the top and changes it to a female. We actually are working with a pulmonologist to actually make sure our images are realistic, but I'll let Amar talk a little bit more about showing these results. What I'm going to do is kind of just switch a little bit and talk about how PRISM can be used for explainability and improving biases together. Okay, so standing back for a moment, that in the field of computer vision, and even a lot in the work that I've done and the work that many of you are doing, we are often interested in this concept of fairness. Is our deep learning model actually working well across different subgroups? Okay, so a big area of research. And we've looked at this as well. So if we say, for example, here's a patient with MS, we have papers on this. This patient will have new lesions in the future. That's something that we've, let's say, predicted from a classifier. We want to make sure, is our model actually working across different groups, different demographic groups? For example, attributes such as race or sex or age are of interest to us. And so we notice here that generally overall in green, we did very well in our model in terms of an F1 score. And if we look at the younger patients, in fact, we do very well. But when we start to look at the older patients, like the one over here that's age 55, our F1 score goes down substantially. And that's referred to as the fairness gap. And a lot of different models were developed in order to overcome this fairness gap for certain demographic groups, okay? However, it's very important to realize that while we took those ideas to some extent, we borrowed them from computer vision, that medical imaging has other areas of fairness and bias that need to be addressed, okay? In medical imaging, we are very susceptible to latching onto spurious correlations in our images. We have classifiers that would say with very high accuracy that this patient has a disease, but if you actually look at what they were looking at, they may have been looking at artifacts, they may have been just looking at things that are common across the population. And the reason is because we have very high dimensional data and not as much as they do in computer vision. And so we are susceptible to this latching. And this is another area of bias that we really need to work on, because otherwise our models don't generalize if that correlation is missing. So let's look at this problem, for example, medical imaging biases beyond known demographic attributes. So here's an example that I think is very telling, where you would have, for example, training samples where, let's say these people all have pleural effusion, but one thing you should look at is what if in our data set, which is very common, we have a lot of devices in our chest. This could be tubes, wires, chest drains, pacemakers, and so on. So if we have someone come in who has a pacemaker who doesn't have pleural effusion, our classifier would actually say pleural effusion because it actually latched onto the fact that it has an artifact. It has one of these support devices in the chest. And that's not right, okay? That has nothing to do with the pleural effusion that you're interested in. So that's an example of what I'm referring to. So the question is, with explainability, can we expose the bias? And other people have actually also looked at some of these aspects of exposing the bias, but now we're also going to try to mitigate the bias, okay? So when we look at, wait a minute, what was the classifier looking at when it came to this conclusion, we hope it was looking in the area of the pathology when we open up the black box. But if it tells us that it was looking at the pacemaker, we know that it latched on to something else. And this is really important because that's the shortcut learning we're trying to avoid. So we asked a whole bunch of questions. All right, here's images. These support devices seem to be a problem. Let's just ask it, can we actually remove the support devices? So last year at MIDL, we actually presented Decodex. The whole point of Decodex was, and this was a diffusion-based model, but we were trying to figure out if we can get over this problem of these spurious correlations. And we did pretty well in trying to ignore them. When we tried to actually remove all of the wires or drains or things like that, the model still did struggle. So what about PRISM? Can we actually remove all the support devices using a single language prompt? And so here we just said, here's a chest x-ray with devices, make it have no devices. So now you can start to see that the wire is gone. There's a clip at the bottom right, it's gone, but other changes are not happening in this chest x-ray. So this is actually amazing because, in fact, it removed all the medical devices for many different contexts. And remember, there's no specific prompt for wires. We didn't have any labels for wires. We didn't have any for pacemakers or anything else. We just called anything a support device. So this is another question. Well, what can we ignore? Does the model actually ignore wires and chest and pacemakers when it's actually looking for the disease? So for example, if we say, here's a patient with cardiomegaly, let's get rid of it. So we can see here that it actually shrinks the swelling of the heart, but the wire and so on was ignored. So that's actually super interesting. The more interesting thing that we're starting to explore, which I think is we're just at the beginning, we're at the beginning of this sort of discovery aspect, is that with these foundation models, can they actually reveal hidden attributes in the images, ones that we didn't explicitly train on? Can it actually find relationships between structures that we didn't actually mention to it? So here's a good example. Here's two different patients with cardiomegaly. They have big swelling in the heart. And we just say, what would this patient look like with no finding, meaning no disease? And you can see the shrinking of the heart. Again, that's really nice. But one other thing that you should notice is that the pacemaker's gone. Okay, other artifacts in other images, whether it's wires, whether it's tubes, they remain, but the pacemaker is gone. Looking a little bit deeper into the literature, we actually found that pacemaker is a treatment for cardiomegaly, and in fact, cardiomegaly can actually pacemaker can actually lead to cardiomegaly, and it's also a pacemaker is a treatment for cardiomegaly. So there's some kind of relationship between them. I don't want to say causal, but there's a correlation that we did not, and we have to keep in mind that we did not actually tell it anything about the pacemaker. And we just gave it examples generally of support device and non-support device. So by having the entire wealth of this data set that Stable Diffusion trained on and CLIP trained on, can it actually pull out these relationships on their own? And what else is it finding that we can leverage? So this was actually presented just a few weeks ago at the Mechanistic Interpretability workshop at CVPR. Happy to discuss this further. So then I just wanted to talk, just a quick plug for another, and I won't go into it at all, for a talk that we're giving tomorrow. John is giving a talk on this work, so I'm just going to kind of shamelessly plug it. And really, this is kind of the merging of its uncertainty and explainability together. And what he's going to be talking about is that conditional diffusion models can actually act as classifiers, and they can. By changing the class, you have different images that are generated, and the reconstruction error can tell you something about the class. And in fact, they have built-in uncertainty and explainability in them. And I was going to say more, but I'd rather just keep you guessing and intrigued so that you will come to his talk tomorrow. Okay, the future is now. This is something I just wanted to talk about at the end of my talk. This is very new work from my lab, and I'm revealing it to you. So two different things that I really want to focus on is this explosion in techniques in MLLMs, which is multimodal LLMs, just went to CVPR, and really that was very, very prevalent, and agentic AI. Okay, so again, we are in the midst of a technology revolution. AI is moving very, very quickly. We are in an age of wonder. And MLLMs, which is multimodal large language models, really have enormous potential for medical image analysis. Okay, they demonstrate a lot of potential aid for clinical decision making. They are intuitive and interactive. So you can actually have ask it questions and change the questions, and therefore easier to integrate into clinical workflow. They can also analyze complex images, and they're inherently explainable. So for example, we can think of problems where we have a report generated or visual question answering, and so on. So here's a question and the MLLM response for this chest X-ray. And again, there's a lot of excitement in this field, but the question we should all be asking is, are they trustworthy? So the first thing I just want to mention is, and I'm sorry about the bottom here, but it's becoming quite well known that these models are overconfident, okay, even when they're wrong. They can be, which is a really big problem, okay, because to be trustworthy, they must be well calibrated in the clinical sense. Okay, they don't have to always be right, but when they are confident, they should be right, and when they're wrong, they should be uncertain. This is what it's been seen in the uncertainty literature. This is very, very important because you could be wrong and say, I have no idea what I'm talking about, but this is what I think, and then the clinician could take it or leave it and actually have some understanding as to whether they should believe it. So what we were looking at is, here's a question. This is from a data set. You can ask me about it after because it's not showing here. But you have a bunch of medical images from three different medical images, and then they say, what kind of image is this? Is this stroke, Parkinson's, MS, Alzheimer's? And the answer is Alzheimer's. The response to a number of these different models was, and here's one of them, the answer was C, MS, with a very high confidence. Okay, so the atrophy in the image suggests that it's MS. It's incorrect, and it's very confident. So misguided trust in an LLM could lead to, of course, patient harm. So one of the things that we're really interested in is actually mitigating this problem. So we're working on and exploring a model based on reinforcement learning, where reinforcement learning is focused on dealing with this miscalibration and making sure that when you're confident, you're correct, and so on, and any other metrics that are actually critical for clinical decision making. And we do that by, just a high level, creating a prompt that will provide a hint that will, in some sense, change the whole accuracy of the outcome and the calibration of the outcome. So this is sort of TBD in terms of publication. So more about that later. And the other thing we found, which is very important, is that there's biases across subgroups for MLLMs in medical image analysis. So this is a paper that we're presenting at MIDL this year, but it's really trying to expose across a number of these MLLMs is that they have biases also across demographic subgroups for classification. There's performance sort of disparities between different subgroups, so in terms of accuracy. So you can have subgroup A, where it's accurate and confident, and another one where it's wrong and overconfident. So again, there's also calibration disparities as well. So this really hinders clinical trustworthiness as well. So just to go through it very, very quickly, what the model we developed is doing is with few-shot learning during inference, not during training. We do in-context learning, and we give it a couple of examples and a query, and we have a frozen MLLM, and we have a prediction and a confidence score, and it basically says, okay, we look at particular attributes, and we start to see if there's some calibration error across different subgroups. Okay, so on the right, you can see it's doing well for females, but it's really not calibrated for males. So it looks at that calibration unfairness, if you will, and we have an algorithm that we've looked at to kind of learn from population calibrations and the subgroup to kind of mitigate and adjust that across different population level groups that you're interested in during inference to deal with that. So we show that we can actually mitigate that gap between subgroups, and that's if you're interested, there's the link to the paper, and also it's available on arXiv. Okay, finally, what would further accelerate adoption of our deep learning tools in the clinic? So here's where things get a bit weird. Okay, so we've all seen this. Let's just look for a minute. Let's stand back as a field and look for a minute at our current deep learning workflow. Okay, so we have a question that we might ask. Okay, here's a patient with MS. What treatment should I give this patient? So that leads to and spawns a number of different tasks that are needed. Okay, so you can imagine a situation where the first thing that we ask is, okay, what type of MS is this? And if I want to classify this image into classes, I have to think, like, let's say I want to deploy it, or let's say I just am asking this question in general. In my lab, I have to find a classifier that works well for this particular task. Should I use ResNet? Should I use EfficientNet? There's these other models. Can I fine-tune them for this task? Are they going to work well? And so on. So I do all this for disease classification, but then we ask, well, wait a minute. How much should I trust this? And as I've shown you today, explainability is a whole other area of research. And so the question is, all right, let's just try counterfactual image generation. Maybe it'll explain why you got to that conclusion. Okay, so now this is a different box that we have to take a tool. Okay, should we use Prism? It sounds really good. There might be other tools, RadEdit. Which one is best for my task? Can I trust it? And so on. And then I'm interested in, okay, well, I also want to know something about the lesion load. That's really important to me clinically. Now, okay, I need to do lesion segmentation. So what should I do for that? Should I use a UNet? No UNet. Should I use MedSam? Everyone's saying that's great. Are they going to work for my task? So all of this is fantastic. In isolation, the tools that we've all developed as a field are amazing. But if you actually look at the workflow, it's very, very problematic. And even though we have all these tools, even for any of us, like if I need to suddenly do segmenting of the brain, I'm trying to think, okay, what's the best one to use? For example, my patient has a lot of pathology. Are these off-the-shelf methods going to work when there's a big tumor in the image and so on? Like, these are things that we all have to think about, not just clinicians. So again, our field has generally, has these like sort of notions of static AI tools. And in every step of the diagnosis process, we kind of have to think about which tools to use, and it's not always clear. And if we change the question, we need a new tool. And so clinicians will have a lot of trouble, and I did actually bring this up when I met with them last week, and they confirmed that this is problematic in terms of their usage of deep learning tools in a dynamic way and in the clinic. So what if we can provide a model that inputs high-level instructions and have it reason on its own and figure out on its own how to provide optimal solutions dynamically? So in comes agentic AI, which is hopefully going to take us from static tools to goal-directed agents. This field is incredibly new. And very new to us, very new to computer vision, and just generally very, very new for outside the machine learning world. And what it can do, it's sort of these agents are these goal-directed agents that can autonomously perceive and plan and act and adapt and accomplish tools in a dynamic environment. So it can it has all of these steps. Okay, so for example, autonomous, you give it a task and it autonomously figures out what steps it needs to actually take to get to the outcome of interest. It's very goal-directed. It keeps the original task in mind as it also starts calling different tools along the way. It's doing planning, okay, meaning task decomposition, and it has memory and learning. So it can actually adapt based on history and data. So it may learn that for problems like this, I'm going to use Prism over RADEdit, or I'm going to use ResNet or MedSam, over other methods. It can actually also, again, it calls these specialized tools, but it actually can also figure out if it's doing a good enough job based on your or a clinician described set of metrics. So the potential is to shift from sort of passive tools to adaptive collaborators. So it's actually quite amazing if you think about it. And there's a lot of promise for agentic AI for clinical decision support, because we can think of it as an agent. So for example, you give it an image and or text, and then the agent can then reason on its own. So decide which tools to use in the toolbox, in what order, self-assess and determine whether it's correct, whether it's calibrated, whether the uncertainty makes sense, can communicate the results, the chain of thoughts of its results, and the confidence at the end in the final result. All of it just kind of laid out. So let me just give you an example, something that we just started playing with, and that's agentic AI for explainability via reasoning. So here we have an input just for fun, because in line with the theme of what I've been talking about, remove pleural effusion and provide a visual explanation. So the agentic AI kind of loop is thought, tool, observation. Okay, so the thought is, okay, I'm going to generate an LLM component. I'm going to generate a medical report to identify pathologies. This goes to a tool. So the tool says, hey, I'm going to generate a report, for example. So the agent takes action by calling these tools. You get a report. The observation looks at the report, reflects on the response, and the report says, blah, 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 right side pleural effusion. So it thinks about the results, adapts its strategy, and now goes to the next thought. The next thought is, okay, right side pleural effusion. I'm going to go to the right side, and I'm going to call a tool to do a bounding box for the right pleural effusion, and then I'm going to look at the results. So then I want to do this, remove pleural effusion. So I generate counterfactuals with a prompt, remove pleural effusion. I call, in this case, RADEdit. RADEdit then produces, let's say, 5 or 6 or 10, whatever you want, different counterfactual images. So think about all the possibilities of what this might look like. And okay, which one of these actually is the right one, the best one for this task? We have all these different results. I'm thinking. The observation then is thinking. How do I evaluate the performance? Which one has worked well? Well, I have classifiers that are telling me if they're actually in the right class. I call a classifier, and I look for specific metrics, SSIM, anything that's relevant to this task, and the difference maps and so on, and I self-evaluate, and then I provide then an answer based on classifier, blah, blah, blah. Here's the final answer. Added pleural effusion on the right lung, counterfactual 2 is best because it had the following metrics that we thought were interesting. Okay, that's one run through one possible kind of crazy world of agentic AI. And I think, again, I brought it to your attention, very, very new and very exciting. But what I just wanted to go back to, and I'll talk about that in a second, is that, again, modern deep learning, I wanted to just sort of specify that we have a lot of new developments. In the beginning of this talk, I talked to you about hopefully showed you something about the tremendous promise of providing clinicians with tools for personalized medicine and trustworthiness and individual treatment effect and causality and so on. There's a lot more work to be done in that space. How do we build causal temporal models with uncertainty across different tests? How do we include other information, for example, genetics or other interesting patient information? How do we kind of look at the balance of risk versus treatment efficacy? And so we're still very much interested in the causal representation learning world, causal discovery. There's a lot that we can do here. But I just wanted to specify at the end that the field's moving super quickly. We cannot ignore it, but we need to proceed in ways that will be helpful. So new developments do have potential for impact in clinical decision support and diagnostic workflow, but I cannot emphasize this enough in that these are really early days, and care is required because both of these types of models that I present raise new questions around trust and safety. The leaders of the deep learning world, Yoshua Bengio has created a new Safety for AI Institute. He is no longer focused on anything else because the power of these models, what we've seen from them is quite frightening in many ways. And so he's working a lot on safety in all elements of safety. But for us, perhaps it's worth just thinking about how they can be helpful and how we can work together in order to make them a lot safer and useful. Final thoughts, and this is me on my soapbox. Apologies for a bit of a lecture. In that, again, for myself, I was reminded very recently about our responsibilities. I went to a Pan-Canadian AI workshop, and there was a CFAR chair who came to speak about the fact that he was very ill. And he conveyed a message which I think I should convey to everyone. It really did impact me. So we are a lot of exciting work in terms of AI, at the cusp of an AI revolution, as I had mentioned, and our middle community has made huge progress and strides and advances, but I just want to remember that we are not just another extension of computer vision. And again, it's easy to forget that we're trying to build tools to actually improve people's lives. So we have to ask ourselves, for all the tools that we are developing, is this actually going to help anyone? Did we design our method and our metrics for success that a clinician would actually, for metrics that are important? Are we collaborating with the clinicians to see what they need, what they care about? And trustworthiness, I feel, is very key to clinical integration. And so he gave a talk which talked about how a single bit changed his life. And that refers to the fact that every test sample, we have to remember, belongs to a patient. And so this is his slide, that on a certain date, he ran a COVID test and it came back positive, and that's when the bit flipped from 0 to 1. And he started with mild COVID, but he ended up with a horrible case of long COVID, which has been debilitating and horrible. And he just wanted to kind of remind everyone that every one of those bits in our test cases is an actual patient. And I pulled this from his slides, that we are the custodians of the best tools to pull meaning from the stars, but we have a responsibility to maximize the benefit to humanity. And so With that, I also, a week later, went to the International Progressive MS Alliance meeting where I met with, they announced a new grant that I received, and really I met with a lot of patients who had a lot of hope for AI in the future. And so I feel like the theme over the last few weeks has been continuous, so I added this to my talk for all of us to sort of think about. And so I thank you for your attention. I want to thank the students that did all this work. And even helped with the slides, and all of our sponsors, and shameless plug that given that I did get a grant, I'm really looking for a lot of new students and postdocs, like 5 new students, effective immediately, and postdocs. I made an announcement on the MIDL job board, but if any of you would like to meet with me or talk with me about possibilities, I'm available. So thank you.
Thank you for the excellent talk. Please come up to the microphones to ask your questions.
Thanks for the great talk. My question is about agentic AI, which sounds like it's a series of AI tools that serially or in parallel are analyzing the results of precursor AI tools. How does one train a system that involves a series of AI tools rather than simply training each tool individually and lumping them together?
That's an excellent question, and there's a long answer. There's a whole set of tools available for agentic AI that, so there's a 2-part question. They are trained somewhat differently. The idea about the planning and the reasoning aspect is this sort of observation module, which keeps in mind everything that has happened and your long-term goals, and also can loop until they are satisfied that they are receiving, that they are basically getting an answer that's effective for those long-term goals. They can, in fact, not just, you can throw more tools, it will start to learn and has memory as to what worked and what didn't work in a broader sense. It can also provide feedbacks to say, perhaps, I need another medical test to be able to get the confidence that I need. Things that you would not have necessarily have noticed. It can actually tell you what it was thinking and what it might need. It can also look at all possible ways of estimating uncertainty, confidence, and so on, and then recalibrate. It's the whole system is meant to be dynamic, but again, you can also bring those tools together for the types of tasks you're interested in. So I showed, for example, explainability. This is where things get even weirder, in that you can have agentic AI models that are focused on different things, and then kind of having multi-agent systems start to communicate with each other, or a higher level agent. And again, it's a longer answer, and I'm happy to show you how the code works, but it's the whole point is that it is in some sense reasoning and learning and getting better at the tasks that it needs to do with time, the more tasks it has. So yeah, things got weird, but it is an exciting time and also a bit of a frightening time. Thanks. Yeah. Hi.
Thanks a lot for this fantastic talk. I was very impressed by your disease trajectory predictions. You're doing this over many years. But I'm wondering, how do you control for confounders? You're predicting patients' trajectories over many years, and people's choices change, life choices change. So how do you control for confounders in this environment?
So thank you for the great question. Are you referring to myself, or like when we design it in terms of confounders? The disease changes and people change and so on. Right now we have a big federated data set of clinical trial data, which is why I'm starting here, where things are unified, there's consistent time points, people are on a trial for a drug and consistently given the same drug, and the outcomes of interest and the tests are uniform. So we're not in the wild west of the clinic quite yet, but if we can get things to work here, and again, when I see here, clinical trials are a finite amount of time. Even that's not great. I need, and I'm hopefully getting, longer term follow-up for patients, because again, it's a window into potentially a 30-year disease. So even that, the data that I have is not sufficient. So yeah, really beginning stages. We have to start with what we know and what the clinicians have done in the trials for now. But I agree that once things get a little more wild, then we need to adapt these. So yeah, I didn't start there. Yeah, thanks.
Great talk.
Thanks.
For all this information. This might be a bomb-throwing question. Why not look at like linear regression? The simple models for this. What's the benefit of deep learning over traditional models? Because when you look at this type of data, right? JAMA, New England Journal publishes a lot of standard models. This factor predicts this disease. This factor predicts this disease. What additional value are you adding other than a very large data set?
Right.
On the input side, right?
So
That's kind of my question. Is it worthwhile at the end of the day, or is this just kind of a shiny thing that we're throwing to the crowd? No offense.
No, not offended. Actually, it's sort of to the whole room. The question's open to the whole room. So yes, there are a lot of headlines that say we have discovered X and Y in medical journals. So for example, MS, let's just take MS as an example. We don't know what are predictive markers of future progression. We have no idea. We think it has perhaps patients with higher atrophy or higher lesion load and things like that. But if we actually focus on features that we know about thus far, we're not going to get anywhere. The whole point of deep learning and big data is that we can start to discover internally features that are predictive of those future outcomes or trajectories. So deep learning is meant to internally learn the features, and they may not correspond directly to just just this feature and just that feature. It might be the co-occurrence of several features, and the personalization aspect of deep learning is the key, because not everyone has the same disease evolution. The population's heterogeneous. If we want to be fair, we have to actually take everything into account and start to learn about subgroups across the population and the heterogeneity, which is not really even how they do anything, even for clinical trials. Clinical trials is...
Then you get into this small population effect, right? You may be comparing your patient with what potentially could be 5 other patients who have similar disease. As a physician, I'd be very reticent to base anything on 5 patients, right? So then...
Yeah, I don't suggest that anyone do deep learning on 5 patients, but I do feel, yeah.
You slice up your patient population.
Yeah, fair. Like,
Males between this age, of this,
oh.
of this, then you start getting into these tiny populations, and you're like, hold on a second. My prediction's based on that. I don't want anything to do with it. Right?
So I never slice anything up. That's the key. So in other words, I'll never say males of a certain age, because it might not be. So I agree with what you're saying, but it might be the fact.
Right? I mean, like you were saying, you do well on females, but not on males. Okay, so then we should slice the model so that we can do well on the females, but not on the males. Or did I read that incorrectly?
So the fairness stuff is how well was it doing overall on these subgroups, but we're still doing deep learning. So the idea is that your model is saying males of a certain age and they present this way in the image, which is something, by the way, that's incredibly important. I'm going back to the title here. Medical images contain a million pixels, millions of pixels. Every single one of that bit of information is adding to our model. And in the clinical world, they don't look at every single pixel and every combination of pixels and so on. So there's a lot of information here that's thrown out in classic, I'm going to extract known features, that deep learning is picking up on. So that's like the important thing about deep learning is it's the discovery aspect. And so so I'm never going to say males of a certain age. It might be males that have few lesions that have, this outcome when they have, this disability score and so on. But it's all internal to our model. That's what I'm trying to say. I hope that answers your question. Maybe someone else in the field actually has a different, better answer. I'm not sure, but that's how I see it. Yeah, thanks.
Thanks. I really enjoyed the presentation, and I like your vision on agentic AI. However, I am wondering about the costs behind it, because I fully agree with you that we have to keep in mind that we're talking about patients and what it means for them. But at the same time, we also have to keep in mind that we have to keep healthcare affordable. And those agentic AI models sounds like we will spend a lot of money on developing that, but also on running them.
So the model that you just saw in explainability, my student worked on for a few days at first before the first results came out. Now, I'm not saying that we shouldn't keep developing and, using the foundation models, using other things, one can get so far, but I don't think that's going to be what's scary to me. What is more frightening is how this might evolve in terms of safety and how will we keep ourselves in check when we deploy them. My thoughts are actually everything I just told you about explainability and uncertainty and so on. We just throw them in there and it will know how to keep everything in mind. So I'm not saying that it's going to do something quite different, but I'm just saying that the safety aspect and the trustworthiness in the clinic is what worries me more than, I guess in this case, the cost. So I'm saying, I guess I brought it forward. These are results that are like a few weeks old, and I'm bringing it here as our first attempt in order to just, throw it out there to the field as something we should maybe keep our eye on and potentially look at. But again, early days.
Thanks a lot.
Yeah, thank you.
Thank you for the engaging discussion, and let's thank Professor Arbel once again. Lunch will be just outside this room.
Yes, if people. So if people could please have a seat, we'll get started soon.
Attention, please. Good. Please get seated. We would like to start with the next session. Thank you. Good.
Okay, great. Thanks, everyone. Let's get started with the generative AI session. Our first talk is style-aligned image composition for robust detection of abnormal cells in cytopathology, and the presenter is Xin Li. You still can't hear? Okay. Okay, so the first presenter of the day is Xin Li. And they will be talking about style-aligned image composition. Maybe talk to that mic. Is Xin Li here? Okay, great.
No, I don't think we can switch now.
Okay. Good afternoon, everyone. It's my honor to be here. I'm Marley from China, and our work is about the style-aligned image composition for robust detection of abnormal cells. Today, I want to highlight a pressing issue in global healthcare. The severe shortage of pathologists, especially cytopathologists, and its profound impact on medical AI systems worldwide. This gap, you can see. Just in that picture, it shows the gap for the shortage is about reach 100,000 to 200,000 by 2025. So the scarcity is very seriously, and the severe shortage of pathology has brought a real data crisis to medical AI. We conduct at CDD the largest public data site for cervical cancer cell detection. It has two important challenges. One is about long detail distribution, and the second one is the staining challenge about the samples. Like the flora, it has different colors in just one line. For about the different labs, different scanners, and different staining methods, and different batches. And this is our method. It proposes a novel training-free style-aligned image composition framework. It's called SICK with 3 steps. Step 1 is at the left. It is in left. It's about the attribute-based selection. First, read each cell's attribute and from a file, and then group all the cell images by their category and types, forming a cell bank, and at the same time calculate the area of each cell from its file name, preparing for the matching, and then performance replacement. First, filter or candidate cells. Those attributes match the target cell. And in our step 2, it's about the style-aligned image composition. As the candidate abnormal cells is selected, we must compose it with a background with preserving identity and style consistency. To end this, first we segment the cell region with some under and center align it. Then extract the visual feature with the DINO-V2 encoder and follow up with visual to test linear projection to get ID maps. Secondly, in our style map extraction, we preserve style by high frequency information. We first select a reference cell from the abnormal cell bank. Those staging steps closely and match the target background using DINO-V2 feature similar. Then we have 2 roads. Road 1 is for self-style align. We use a candidate's high frequency map directly. Road 2 is for the background style. And in the background style, we blend the 2 maps with a weight alpha to retain K cell structure. Finally, these high frequency maps combined with the shape mask and filled into the control node to generate style maps, providing detailed styles get for the subsequent style transfer to the new image. And at last, we feed it to GPT, and it will give us the answer, which is much more masked, and which is a great one, and we can choose as the answer. For these 4 tail catalogs, we use TSNE analyze on the style distribution of the training size, augmented size, and test size. As shown in Feature 3, our seek especially complement the staining style and in the training set, and we enhancing the detection robustness to staining various. In Figure 4, our seek images with high FID and rich information density. As shown in Table 2, compared to other methods, our seek outperformance all our FID and DINO-V2 scholars. And we conducted a user study with 8 doctors to evaluate the quality of seek. The average accuracy of distinguishing real from the image was 50%. These results demonstrate that the images are realistic enough to support doctors to do the diagnostics. That is the user studies results. As shown in Table 1, seek achieves the best average improvement across both detection methods, especially for the tail categories. For example, flower improves by 15 points on YOLO and 11 points on faster RNN. And this picture informed that every part of our method is very useful for the qualities of the results of the study. And to demonstrate deployment efficiently, we stress that the argument is only used during training and does not affect inference, speed, or memory. So SIG generates each argument image in just 60 seconds without fine-tuning, and its delivery support a great quality. And to better confirm SIG's ability, we expanded the cross-domain analysis. Results show that SIG achieves great FID in other 3 tabs, and highlighting its possibility for broader tabs of the cytophyologies. Finally, let me summarize our work. We have proposed a data argumentation framework for cytophyology abnormal cell detection. Our style-aligned image composition SIG framework offers several advantages, including being training-free, style-aligned, and high fidelity. SIG presents a breakthrough in cytophyologic image argument, providing a robust and adaptive solution to enhance the robustness and adaptability of the medical AI models. That's all about my report. Oh, that's my. You can you can connect me in that code. That's all.
Okay, please come up to the microphones if you have a question. I can ask a question, perhaps. I'm over here.
Okay.
Sorry. Yeah, the high pass filters that you have in your style alignment. Can you give us a sense of like what type of filters you used, and how did you decide on the filters that you put into the model there?
We have several filters. One is about the category and type and area, and then we have other like the we use DinoV tool to extract its ID maps, and we feed the ID maps and the style maps together into the diffusion, into the stable diffusion, and we control the input, make it make the image just like we want. Yeah.
Okay. There's no other questions. I will move on to the next talk then. Thank the speaker one more time.
Okay, thank you.
The next talk is Lotus latent outpainting diffusion model for 3-dimensional ultrasound stitching. Now, so I have to. Yeah, perfect, thank you. Why is it? is Mohammed Alas. Here? Ah, thanks. Quickly have to figure out how to get now your PDF there.
It's okay. Am I the only one with the PDF?
It seems so.
I'm sorry.
All good. If you need the pointer, just there to get this.
On the slides with this one, right? Thank you so much.
But there you can of course also.
I think, can you go back to, sorry. Are you in Google?
No.
Okay.
I think you have to open it as
Let me
a
do something. No. Open with Google. I think in Google is easy. Okay. I think if I go here and I press present, that's me.
Maybe they only shared PowerPoint there. That I think. Can we move it just to the other side?
yeah,
So
maybe.
maybe just exactly like this.
Okay. That works.
It's maybe not perfect, but at least it could work.
Okay, here we are. Perfect. Okay.
The floor is yours.
Okay, thank you for your introduction. Thank you, everyone. Hello, everyone. Thanks for attending this talk. And I will be presenting you our team project, which is titled Unveiling Differences, a vision encoded decoder model for difference medical visual question answering. This project has been developed at the PRHLT Research Center in the Universidad Politécnica de Valencia in Spain, in collaboration with my colleagues. My name is Mohammed Salas, and I will be walking you through the key points of this project. Let's start with an introduction to the task we will be solving, which is visual question answering. This is a multimodal task that combines both computer vision and natural language processing. The goal, as you can see, is to answer a natural language question based on a visual input, in this case, an image. And unlike another vision task, this task requires reasoning over both visual and textual input, as I've mentioned. If we take a look at the picture, there, and taking into account the question, is the girl walking the bike? If we look at the first picture at the left, then the answer should be no, because she's indeed not walking the bike. On the other hand, if we take a look at the picture on the right, then the answer should be yes. To be more specific, we will be targeting this subtask, which is difference visual question answering. And the main difference with the previous task is that it focuses on comparing two or more images to answer the question. The objective is not just understanding one single image, but understanding the differences, the visual differences between two or more of these images. This is obviously a more complex task because we need fine-grained alignment between the images, so we can correctly analyze the differences between the images. All right, here are some key contributions in this field to this problem. We have graph-based model like ACADE. We have dual transformer approaches like AIE. Another tried retrieval augmented approaches like Regiomix, and we have also multi-stage training like Plural. Our work, our model aims to simplify these models because, as I will be mentioning, they have a problem, and it is that the decoder, the part that generates the answer, the text, is usually very big. It has a lot of parameters. They use huge transformers, GPT-like transformers, and we will try to simplify that. And if possible, we will try, obviously, to improve the performance. So if you can look at this picture, this is the model we present, which is a vision encoder followed by a transformer decoder. For the vision encoder, we choose swing transformer. I will explain why that later. The output tokens of the vision encoder are fed by cross-attention to the transformer decoder along with the question tokens. And then the transformer decoder will generate autoregressively the answer tokens, which means that for each token generated, it will be taken into account the previous tokens. We also add a differentiation component, which is really important, and I will be talking about each part in detail right now. Let's start with the vision component. So first of all, as I said, we chose the swing transformer because it has a great performance in many vision tasks. Its hierarchical design and shifted window attention makes it well suited for X-rays, which is the kind of images we're using. We are using the radiographs of the MIMIC dataset. I will talk about that later. And to be more specific, we will be using the swim base, pre-trained on ImageNet 21K and fine-tuned on the MIMIC dataset. Let's talk now about the differentiation component. This is a very important part of this model. We like to call it image differentiation embedding, ID. This basically will help the model differentiate which is the main image, the main radiograph, which is the most recent one, and the reference radiograph, which is the one taken in the past. And this is important because imagine that the main image, the disease has gotten worse, the patient is worse, and the question is about that disease, then the answer should be that this disease is worse now. If we look at the reverse case, then where in the main image the disease has disappeared, or in the case that the patient has gotten better, then the answer should be that the disease is disappearing, the patient is better. That's why we need to help the model distinguish between the main and the reference image. We do this by two learnable embeddings at the training time, which are added to the tokens of each respective image, the future tokens that are the output of the vision encoder. Those are trained jointly with the model, and they are fixed at inference. All right, to finish with the model, let's talk about the language component. We decided to do simply a 3-layer transformer decoder, and I will explain why is that later when I talk about the data set. We tried with 2 layers, but this, as you can see, degraded the performance. And we tried with 4-layer transformers. This didn't give any improvement, and we were looking for efficiency, so we kept the 3-layer option. This was great because it let us have 51 million parameters only, which is a really lightweight decoder in comparison to other proposals, as I've mentioned, which use huge transformers, GPT-like transformers. All right, let's talk about how we trained the model. We did it in three stages. Stage 1 was taking the swing, pre-trained already in ImageNet 21K, and fine-tune it on the MIMIC radiographs using the checkbird label. The checkbird labels basically tell us which are the diseases that we can find in each radiograph. With this training stage, what we wanted to do is to already have a swing that has knowledge on these radiographs, and in the next steps, it will help us to generate accurate answers to the questions. In the second step, we trained the whole model, but with the swing frozen. So we take advantage about this knowledge that the swing already has. And this way, the decoder will learn to generate these answers correctly. And for the last stage, we unfreeze the swing, and we train it all together for a few more epochs. As you can see on the table below, how each stage improves the scores for almost all the metrics. It's important to notice that by adding in the second line of the table, the ID, the image differentiation embedding, we get a noticeable improvement in the scores for all the metrics. So yeah. Now let's talk about the data set. I know I've mentioned that we are using the MIMIC data set, which is partially correct, but to be true, we have been using the medical difference visual question answering, which is an extended data set, and synthetic extended data set on MIMIC, which uses the same radiographs of MIMIC, but MIMIC is a data set of radiology report generation, which has reports. But in our case, the medical difference visual question answering has questions and answers, which is what we were looking for. This data set has 7 categories of questions, as you can see there. But since we were targeting the task difference visual question answering, we took only the difference questions. It is important now to take a look about how these questions and answers look like. So they follow a template. So the questions can be, what has changed compared to the reference image? And the other option is, what has changed in this specific location? What has changed in the left lung area, for example? The answers are open-ended, yet repetitive, as I have said, because they follow a template. If nothing has changed, which is not normal, usually like in the training set, there's almost every time there's some changes. So, but if there's no changes, the answer is nothing has changed. And if there changes, it would say the main image has additional findings of this finding, this other finding, this other finding. Perfect. Okay, I know you're probably tired of this image already, but let's get to the results. Once we trained our model, we obtained our results. We decided to benchmark with the state of the art. And we were quite surprised because we improved all the metrics, almost all the metrics, but Meteor. And that was quite impressive because as I've mentioned, we are using a quite light decoder with only 51 million parameters in comparison to other proposals which use huger ones. This is a finding that it is important, and we would like to inform you about that standard metrics like Blue, Meteor, or Rogue can give high scores to model predictions that are clinically incorrect. And that's because these metrics measure linguistic similarity, not clinical accuracy. If you can see, I have a case at the right, case at the left, and case at the right. Okay, so the case at the left is quite accurate. The prediction is almost perfect. It predicts all the clinical diseases perfectly, almost perfectly. But the case at the right, the clinical diseases are not predicted, are predicted incorrectly. But still, these metrics give high scores to both cases, and that's because in the answer, the clinical relevant text is maybe 15%, 20%. So even if these predictions are not correct, then the global score will be high, as you can see in this slide. We even get a higher blue one on the not so well predicted case than the well predicted one. And to finish, let's summarize our contributions. With only 51 million parameters in the decoder, we get a really efficient, lightweight decoder. We introduced the image differentiation embedding, which helps the model differentiate between the main and the difference image. The main and the reference image. Yeah. Despite the lightweight architecture, we are able to compete with the state-of-the-art, also apporting a more efficient, simplified model. And to finish, it is important to underline the need for domain-specific metrics that really tell us if the answer given, or not just the answer for this task-based question answering, maybe for radiology regeneration, we need metrics that really tell us if the answer or the report is the predictions that, the clinical predictions, sorry, are correct, because that's the main point of this task. So yeah, thank you so much again for attending this talk. If you have any questions, please do not hesitate in asking me, and yeah, I will be glad to answer all of them. Thank you so much.
Thanks for the presentation. The floor is open for questions.
Thanks for the nice talk. I'm
Thank you so
glad
much.
you appreciate the problem with using Blue, Meteor, and Rouge for analyzing the quality of clinical text reports. In our experience, those metrics are pretty much useless.
Yeah,
because
nowadays.
they don't assess clinical accuracy. I've worked with a postdoc fellow from another lab at NIH named Qingqing Zhu, who has developed new metrics, which I'd encourage you to take a look at. If you have trouble finding her paper, don't hesitate to reach out to me.
Okay, I will definitely. Thank you so much. Thank you so much.
Yeah. Great talk. So I have
Thank
a
you so
question
much.
regarding your training stages.
Okay.
So you use 3-stage training. So what if you do not use the second stage at all? That means decoder pre-training, and use the encoder pre-training, and afterward use the full model at a time fine-tuning. So how does that perform? So did you check that one?
Sorry, can you repeat again?
So you have 3 stages.
Okay, yeah.
So you first do the pre-training of the encoder, then you pre-train the decoder only,
Yes.
and then you do the fine-tuning
Exactly.
of the whole full model.
Yes.
So what if you do the pre-training of the encoder and do not do the pre-training of the decoder
Alone.
But yeah,
Unlikely
you go to the third step and you run for like more epochs, train for more epochs or fine-tune for more epochs.
You
Is there
mean
any
why
difference?
I don't jump to the third stage directly?
Yeah, yeah.
Okay, we did this because as we fine-tuned the swing transformer, and if we directly, without freezing it, then we would lose this training. You know, we wanted the decoder to learn to answer the questions with the knowledge that the swing transformer already learned. That's why we did the second step. I don't know if that answers.
Yeah, I understand your point, but my question is, did you check whether if we actually do the fine-tuning, like first step and the third step, not the second step, is there any difference in accuracy or anything?
We thought of this plan. We haven't tried like the thing you mentioned. I think our approach is better, but obviously I don't have the numbers, so probably you're right, and I should have tried the other
No,
thing.
it's fine. Thank you. Thank you so much.
You're welcome.
Please, one short question and also
Okay.
short answer.
Okay.
If we are looking for differences, why wouldn't a registration algorithm work if you have the same patient over time?
Yeah.
Can I find the differences by just doing like registration amongst the scans?
Register. What do you mean by
Like
register?
just register the 2 images because these are same patients.
Yes.
And then I can find the differences in the pixels or maybe in a region. Like, why wouldn't that work?
Yeah, that's what we're trying to do, like with the.
But there is no registration here, from what I understood, right?
I mean, we're taking the filters. We are extracting the filters of each image.
Okay. Maybe I can follow up later.
Otherwise,
No. Okay,
exactly,
sorry.
we
We can
discuss
talk now
later
in the
on the
poster.
poster.
Okay.
Let's thank the
Thank you,
speaker
sorry.
again.
Okay, thank you so much.
Okay, our next talk is MedVAE, Efficient Automated Interpretation of Medical Images with large-scale generalizable autoencoders. Our presenters, I think, are Maya Varma and Ashwin Kumar.
Okay, hi everyone. My name is Maya, and today Ashwin and I will be presenting our recent work, MedVAE, where our goal is to create large-scale generalizable autoencoders to essentially downsize medical images and improve efficiency of our downstream computational pipelines. Both of us are PhD students at Stanford University, and we're very excited to be here today. All right, so unlike natural images, medical images often include very small features, and as a result, they must be acquired at very high resolutions. So for instance, rib fractures in chest x-rays are often very small, and so are microcalcifications in mammograms. And as a result, these types of images must be acquired at these high resolutions so that physicians can accurately interpret these features. Now, the issue is that these high-resolution images often incur significant storage costs when we're storing them to disk on our computers. And they also require very high computational complexity when we provide them as input to our downstream models. And these kinds of issues are likely to become significant challenges in the coming years, especially as the volume of medical images being stored by hospitals continues to increase, as well as these more recent paradigm shifts that we're seeing towards very compute-intensive foundation models. Okay, so the current gold standard for downsizing medical images is a strategy called interpolation, which is very frequently used in the field of medical imaging. The idea here is essentially that we compute the value of each pixel as a weighted average of its surrounding pixels. But the challenge is that this kind of approach can cause us to lose those fine-grained features that we talked about earlier, like those rib fractures and those calcifications. And so quantitatively, on a calcification detection task, we can see fairly substantial reductions in performance as that downsizing factor of those images increases. And so overall, we can pretty much assume from this plot that the downsized images are exhibiting poor quality. Similarly, if we wanted to take those downsized images and try to reconstruct back that original high-resolution image by applying interpolation in the other direction, we can see that, again, we're losing those fine-grained features and really generating these low-fidelity images. And so, again, we can assume that those reconstructed images are fairly poor quality. And so our goal in this work is to address these two challenges. So we want to be able to downsize medical images in order to improve the efficiency of our downstream computational pipelines, but while also ensuring that these small, fine-grained features are retained in both those downsized images as well as the reconstructions. And so in order to accomplish this goal, we're introducing MIDVAE, which is a suite of large-scale autoencoders, so specifically 6 large-scale autoencoders, that are designed for downsizing 2D and 3D medical images. The overall architecture of MIDVAE looks something like this. So the idea is that you'll take your original source high-resolution image, you'll pass it through some sort of trainable encoder, and generate a downsized latent representation. That downsized latent can then be passed through a trainable decoder, and that will yield a reconstructed image on the other end that is hopefully going to look very similar to that original source image. Now, the idea is that these downsized latent representations can be interpreted as downsized images, and we can use them as part of our downstream computational pipelines instead of those source images, which will give us a lot of benefits in terms of efficiency. So if we assume that the area of those source and reconstruction images can be expressed as h by w, then we can say that we apply a downsizing factor of f, which will reduce the 2D area of that downsized latent representation by a factor of f. So concretely, as an example, if we were to assume that f equals 16, then that means that the dimensions of that latent representation would be h by 4 times w by 4, which will essentially reduce that 2D area of the image by a factor of 16. Now, this kind of logic could be easily extended to the 3D setting as well. So continuing on with this example, in that particular case, the 3 volumetric dimensions would each be reduced by a factor of 4, leading to a total volumetric downsizing of 64. All right, so in order to actually train MIDVAE, we introduced a 2-stage training procedure. So the first stage of MIDVAE involves essentially maximizing that perceptual similarity between that source image and the reconstructed image. Now, while a lot of existing strategies for training autoencoders typically stop at this stage, so for instance, the stable diffusion approach for training autoencoders uses only this first stage of training. So instead of stopping there, we're actually introducing a novel second stage of training that is specifically designed to refine that latent representation space and preserve those clinically relevant features. So in the 2D setting, the way this works is we're going to freeze that encoder and decoder that we trained in the first stage. And we're going to add a subtle refinement step in order to improve that quality of that latent representation space and make sure that we preserve those clinically relevant features. And we're going to do that by introducing a guidance mechanism during training using an external 2D foundation model called BioMedClip. So concretely how this works is we're going to take that latent representation, pass it through a series of lightweight trainable projection layers, and then apply an embedding consistency loss function based on BioMedClip, where we're essentially forcing that latent representation and the source image to be consistent with each other in the embedding space of BioMedClip, meaning that hopefully those clinically relevant features will be preserved. Now, in the 3D setting, what we're going to do is we're going to take that stage 1 architecture that we trained, and we're going to lift it up to 3D by applying a kernel-centered inflation strategy. We're then going to perform continued fine-tuning using a large collection of CTs and MRIs, so 3D imaging. And the idea is that this fine-tuning procedure will enable that latent representation space to capture volumetric features. So ultimately, at the end of this 2-stage training procedure, we'll end up with these downsized latent representations that we can use in place of the source image in our downstream computational pipelines, which will help us improve efficiency while also ideally preserving those clinically relevant features. All right, so we train MIDVAE on a very large-scale data set that we curate, which consists of 1 million 2D and 3D medical images collected from 19 open-source multi-institutional data sets. And the composition of the training data is shown on the screen here, and it essentially encompasses X-rays, mammograms, CTs, and MRIs from a variety of anatomical features, which essentially encompass the entire human body. And our key intention with trying to train on such a large-scale data set was to make sure that our autoencoders would be generalizable, which means that we want those downsized latent representations to be useful in a wide variety of downstream clinically relevant tasks. Okay, and I just wanted to provide a visualization of what MedVAE actually looks like in practice. So this is an example of 3D MedVAE with a downsizing factor of 64x, which means that each of those volumetric dimensions is each reduced by a factor of 4, leading to a total volumetric downsizing of 64 times. All right, and I'll now pass it to Ashwin, who will discuss some of the results.
Awesome. So we evaluate MedVAE on 20 multi-institutional data sets across 4 different imaging modalities and across 8 anatomies. In order to demonstrate that MedVAE meets our goals, we conduct evaluation across 3 axes. First, we want to ensure that our latents preserve clinically relevant features. To do that, we compare downstream model performance across a series of classification tasks trained with the source high-resolution image and the downsized latent representations. We first evaluate latent quality in the 2D domain, where we have 5 clinically relevant tasks, out of which 3 are 3 mammogram-related tasks. These include malignancy and calcification detection and BI-RAS prediction. We also have 2 musculoskeletal tasks, which include pediatric bone age prediction and wrist fracture detection. And these tasks were chosen since the findings are subtle and fine-grained. We can then compare the original high-resolution image versus the downsized methods. These methods include interpolation, as well as general domain natural image autoencoders, which is stable diffusion in our case, and our 2D MedVAE model. These methods had a 4 times downsizing in each dimension, leading to a total of 16 times downsizing. And we note that 2D MedVAE outperforms the general domain autoencoder by around nearly 8% on average across these tasks. Interestingly, MedVAE also outperforms the general domain autoencoders on the 2 musculoskeletal tasks, despite the fact that no musculoskeletal radiographs were used during MedVAE training, suggesting generalizability of MedVAE. We then evaluate our 3D latent representations on 3 clinically relevant tasks, including spine and head fracture detection and ACL/meniscus tear detection. These tasks were selected to contain findings that exist in multiple slices or are volumetric in context. We compare 3D MedVAE among analogous baselines, as in the 2D setting, at 4 times downsizing in each dimension, leading to a total of 64 times volumetric downsizing. We note that 3D MedVAE outperforms the general domain autoencoders by over 12.5% on average across these tasks. And the main takeaway in both the 2D and 3D setting is that these downsized MedVAE latent representations can be used as drop-in replacements for the high-resolution image in these downstream pipelines while either maintaining or exceeding performance. We can then move on to our second axis of evaluation, where we evaluate whether these latents afford efficiency benefits. We observed that in the 2D setting, MedVAE latents can reduce the time to perform a forward pass from over 14,000 milliseconds to 204 milliseconds. Furthermore, for the same GPU size, we can increase the batch size from 128 images to 4096, a 32 times total increase. In the 3D setting, we note an around 62 times reduction in time to perform a forward pass, as well as batch size increases that are proportional to the downsizing factor. In this case, for a 48 gigabyte GPU that can potentially hold 32 3D volumes in the batch, we can now use MedVAE latents to fit thousands of images in a batch. And the main takeaway is that these latents can improve training efficiency. We now move on to our last axis of evaluation, where we evaluate reconstruction quality. To assess whether clinically relevant features are preserved in the reconstructed image, we supplemented our automated evaluations, which can be found in our paper, and present here our manual reader study. We had 3 radiologists review and score chest x-rays with rib fractures in them. And this is an example figure of what those radiologists saw. On the left is the original image, and on the right is the reconstructed image. And they were evaluated for image fidelity, preservation of diagnostic features, and artifact presence. Our methods were compared on the 5-point Likert scale, which ranges from -2 to 2, where 2 suggests a preference for that method on that criteria. And when we compare interpolation and 2D MedVAE on our total downsizing factor of 16, we see an over 2-point difference between the 2 methods, with MedVAE showing comparability to the original image. We note even greater differences between the two methods at greater downsizing factors, with MedVA still showing relative similarity to the original image. Our main takeaway here is that these MedVA reconstructions can preserve clinically relevant features. In summary, we show that these MedVA latent representations can replace the high-resolution image in our downstream pipelines. We also allow for MedVA latents to have reduced storage and also improve training efficiency, and that these MedVA reconstructions preserve clinically relevant features. So we think about in this real-world training setting, you can save your latents for your original high-resolution images, and if you ever want interpretability, you can use our decoder to bring it back to this original space. In future work, we're excited to potentially train foundation models using latent representations instead of the original high-resolution image, especially in academic compute-constrained settings. We're also excited to potentially train additional training strategies to improve latent quality at higher downsizing factors. We would like to acknowledge our funding sources, which made this work possible. We're also very excited to share that MedVA is fully open source. Our code is available on GitHub, and our models are available on Hugging Face. We're excited that there's been significant community interest in MedVA so far, with over 9,000 downloads to date. Our pipeline is really easy to use on GitHub. There's an easy-to-use inference engine in which MedVA is a class, and you can instantiate your own models with it and adapt in your own PyTorch pipelines. And super easy to install with just pip install MedVAE. We also allow for support for fine-tuning MedVAE on your own custom data sets. And if you have any further questions on this, please feel free to email Maya and I at our emails. And meet us at the poster session. Thank you for paying attention. We'll open up to questions now.
Yes, go ahead with questions, please.
I'll just speak out loud. So I understand that for the 2D part of the image, you're based on the pre-trained biometric model, which I believe was trained on a PMC dataset, includes like image and caption pairs. So for all the datasets that you have tested on the MedVA afterwards, do you know if any of the datasets you tested were like out of the dataset that were free from any potential data corruption?
Yeah, so the data that was used for training Biomed Clip was, like you said, primarily PubMed data. And so these medical images that we're using from, multi-institutional data sets that are collected in clinics are not part of the training set for Biomed Clip. And so as a result, although some of them might be in domain in the sense that those kinds of images might show up in PubMed, those exact data sets were not used during training. Thank you.
Over here, on the other side.
Hi, wonderful work. I'm just curious, if I understand correctly, in a stage 2, when you use Biomed Clip to align the latent feature and the original image feature, you're only tuning the projectors, not the encoder-decoder, right?
Correct.
I'm wondering why don't you? The point is, there's a chance that the original encoder-decoder compression can potentially already suppress some important information because you were originally saying the fine scale structures could be lost, right? So it feels like contradictory to what you're saying in the beginning.
Yeah, that's a really good question. So the reason we ended up splitting it into these two different stages of training was we really wanted that first stage to focus on reconstruction quality. So we wanted to make sure that reconstructed image was as close to the source as possible. And then that second stage would go ahead and refine that latent space using a additional guidance mechanism with Biomed Clip. And as to your question as to why we didn't specifically fine-tune the encoder and decoder for that second stage, we noted that refining the latent space there and applying those Biomed Clip penalties during training would actually degrade the quality of those final reconstructions. So we wanted to essentially separate those two components and specifically target those stages of our training pipeline to directly match those two goals we're looking at, right? So the first stage specifically optimizes for reconstruction quality, and the second stage specifically for latent representation quality.
But, okay, just one more question, like in a grander scheme, right? The whole point is you are saying is to compress the image while focusing on the clinically relevant information. In a sense, it shouldn't be a compression in the sense of image compression. it's more like compression in the sense of preserving critical information without losing them, right? So yet probably it's not a question. It's just a, yeah.
Okay,
So-
you have something to say in response to that?
I
Go
can
ahead. Yeah, go
respond
ahead.
really quickly. So yes, that's correct. So we do want to preserve those features, but we're really looking at what would be the real world use case of something like this, right? So the idea would be that a user could use this pipeline to compress their image and pull a downsized latent representation that they can use in their downstream pipelines. But then if they wanted to, go back and have a radiologist read the image, we allow the user to essentially plug that downsized latent back into our pipeline and decode back that high resolution image. So the idea was to essentially maximize the quality of both those stages so that users could use this in their pipeline, as part of standard clinical practice.
Okay, sorry, we're out of time. We're over time for questions. For everyone still in line, we'll have to take it offline with the poster session.
Thank you.
Thank you.
Thanks again.
Great, then after already having received quite some teasers by Tal earlier on, we now get the full details on PRISM by Amar Kumar. Where is my, yeah? Perfect, and here you can also click and have a button.
Okay, perfect. Hello, everyone, and thank you for attending this talk. I'm Amar Kumar, a PhD student at McGill University and Miller, and I'll be presenting our work, PRISM, High Resolution and Precise Counterfactual Medical Image Generation using language-guided stable diffusion. Before I begin my talk, I would first like to thank all my co-authors, Anita Kriz and Mohammed Hawaii from Google Research, and also my supervisor, Tal Arbel. Let's talk about the fundamental problem in medical AI and the medical AI reliability crisis. We see a lot of deep learning models being deployed for various tasks from segmentation to image generation, classification, detection, and the list goes on. But the primary question that we need to address are why are deep learning models not reliable for medical imaging tasks? Some of the reasons I've listed here, but the list is non-exhaustive. The primary being spurious correlation, where instead of looking for relevant things in the image, the model starts finding shortcuts and associating these shortcuts with the decision of the classification. There is a huge problem that is associated with data imbalance. We cannot have a perfectly balanced data depending upon how images were acquired or collected, so this entire domain of medical imaging suffers the problem with data imbalance. There is a lack of transparency, although we see different models coming out and showing variability in performance, also some with great performances, but we don't know if the decisions are interpretable. And finally, limited annotations that is present for the data. So we don't have enough textual descriptions that is available for most of these tasks. Now, let's imagine a clinical scenario. A chest X-ray of a patient is being given to a deep learning model, and the decision is the diagnosis is pleuroeffusion. But the critical questions that we need to ask is, first, is the decision correct? Second, is it right for wrong reasons, which essentially means that even if the decision is it right for correct reasons, or is it looking at something else? And finally, what about personalized disease diagnosis? We cannot ignore those. So talking a bit about the traditional approaches to explainability, and here I'm restricting myself only to image-based explanation and not textual explanations. There are post hoc explanation methods like LIME, SHAP, GradChem. I'm pretty sure most of you are familiar with this, and there are even more. I have not cited all of them. Then there are a different kind of explainability for the network, which is given by AtriNet and GIFsplanation, which is latent space-based manipulation. And they try to explain the image by observing a difference between the factual and the counterfactual images. And finally, the counterfactual line of argument, which is essentially asking this question: what minimal change should be made to the image and under what scenario, such that you are able to alter the outcome of the model that you're looking at. One such example of a model is Decodex, which is published by us. And the solution to this is having a high-capacity generative models. So from here, we shift into understanding a bit more about this counterfactual image. So let's say that you're observing a patient who is sick, the same as the previous example. Essentially, what you're asking is, what would this patient look like if it were healthy? So imagining a counterfactual scenario, what if it was healthy? So on the leftmost side, you see the original image, which has been given into the model. The middle image, which is a counterfactual generation, it does not exist in reality, but it's addressing this constraint that what if this person was healthy? And if you take a difference map of the two, you can essentially see that it's trying to associate this difference map to the region that is responsible for the decision mechanism of the model. And this counterfactual image generation is done under these three constraints that are mentioned over here. So shows minimal change with respect to their factual counterpart, belongs to the correct target class, and also shows realistic changes. And with the development of foundation models, it has offered a new paradigm, which is essentially bringing general artificial intelligence to specialized medical imaging applications. And why are these useful? It allows us to do high resolution image generation, which is what we are doing in this prism. We are also able to use language guidance, which essentially means natural language guidance, to have control over the image in whatever way we would like to have. And finally, leveraging this information from transfer learning, which is because these models are essentially trained on massive training data sets, which are also diverse in nature. So essentially, what we are trying to say is intuitively, they should also have enough semantic information, although not trained on medical data. They will have decent amount of semantic information that can be associated. So what we do is Prism utilizes a backbone of Stable Diffusion 1.5, which is an open source foundation model. We take the pre-trained image encoder and the pre-trained clip encoder, so literally just taking off-the-shelf Stable Diffusion 1.5 and fine-tune it for the purpose of medical image generation. This image encoder, it's rich enough in visual understanding. There is general image understanding of what a medical image looks like. There is also robust feature extraction. In terms of what clip brings to the table, that's more about language understanding and also image text alignment. Once these two are tuned, what do we get in the end? We get a vision language model for medical imaging where the model has information about medical domain knowledge, clinically relevant knowledge, anatomical precision, and also pathological understanding. So let's look into detail how does this prism work. And we have the main architecture of Stable Diffusion itself. We are not modifying that. So this prism, it takes two inputs, which is your image and text pair. Over here, an example is shown, an image being passed through the image encoder, which is frozen, and also a text, which in this case is chest X-ray of a patient with lots of medical device. Once these two, which is the VA encoder and the clip encoder, both remaining frozen, is passed through the architecture of Stable Diffusion, only the central part of this denoising process of the unit is trainable, which is shown over here. Once that part is trained, it's also passed through the frozen decoder. So if you do not change the text, which essentially means if you don't give it any edit command, essentially it should just be inverting the image. So as a baseline, we show that our inversions are pretty good. And if you're interested, you can read the paper. We have shown a lot more of these inversions. But this is not what we want. What we want is at the time of inference, having the capability to change or make edits using language. So over here, the edit text that is given is chest X-ray of a patient without medical device, the difference being highlighted in green. And when passed through the same architecture, you can notice this location where it's able to erase that medical device. Now, this is pretty interesting to us because we never told what does medical device mean. We never specified where does this medical device lie. And it was able to understand this semantic information from the fine-tuning process directly. On top of this fine-tuning method that I explained, Prism also has a kind of a quality control check, so a bit of math, which we essentially call as clip score, which is popularly used in literature. So it is essentially a norm of the image editing difference and the text editing difference, which is given by this equation. Essentially, intuitively, what it's doing is you have the original image, you pass it through the image encoder, you get a representation. You have the counterfactual image, take that, pass it through the image encoder, and you just take a difference of the two. And similar thing is done for the text embedding difference, same thing for the text. And if this clip score is less than 0.1, we find that the editing is not good, so redo the entire task again, and you're able to obtain a very high resolution image edits. So in terms of the capabilities of Prism, what are the things that it's able to do? It can do image generation at 512 cross 512 image resolution. An example being shown over here, chest X-ray of a patient with severe cardiomegaly, which is abnormal enlargement of heart, occurring in the center of the chest X-ray with lots of support device. So you can see that the image resolution is pretty good. And this is a synthetic image. On top of that, it allows you to have selective attribute control, so it is able to modify specific feature with the semantic understanding from the knowledge and also performing this counterfactual image synthesis for explainability. An example is shown over here, same text, chest x-ray of a patient with lots of medical device, and you can see that all these medical devices are erased. And here are some more examples which talks about the diverse nature that it can edit. Same text, just remove devices from the image, and in this magenta box that is being shown, and also compared against a baseline method, which is a GAN-based classifier guided method. So those methods are unable to even perform this task at almost the half the resolution, which is at 224 cross 224. Over here, we show the capability of PRISM to explain the disease, and you can notice in the difference map that how finely it's able to show that difference map and also relate to this original and edit text being shown on the left-hand side. It can explain diverse diseases, so not only cardiomegaly, but also pleural effusion and many more that is available in the data set. And all that can be analyzed by seeing this difference map that we have in front of us. On top of all the capabilities that we talked about, it is also able to ignore the confounder. So if there is radiologist among us, you should be familiar with pleural effusion occurs in the costophrenic angle of the lung, which is essentially both of the bottom corners of the lungs. And this example is deliberately chosen because you can see there is a lot of wires in the costophrenic area. And the model ignores the wires, and essentially in creating a healthy patient, it's able to correct the particular regions that is associated with the disease pathology. So this is what I was mentioning at the beginning, to be able to ignore this and look at the regions that are essentially responsible for disease pathology. On top of all this, what do we do with these images? They look pretty, they are nice, they are aligned, they explain the images. They can be used to develop robust classifiers. So over here, if we talk about the task of classification of multi-head classification of disease, 4 being shown here, pleural effusion, cardiomegaly. No finding is essentially healthy and support devices. If you look at the first row, that's the performance of a multi-head efficient net. And if you perform a data augmentation strategy on top of the original data. So if you just randomly sample from stable diffusion, you don't notice any improvement. But if you synthesize counterfactual images from PRISM, you notice there is a clear difference between the accuracies that are reported for each of these tasks. Thus, PRISM can synthesize images that are helpful for improving the performance of downstream classifiers. Now to wrap all this up, how does it perform with state-of-art models that are available out there? So we take the models that are given by some other approaches like RADEDIT and Imagic. Also, we are comparing it to null text inversion. And again, if it's not super clear, you can notice in the box that other methods are unable to edit these images clearly. So we perform way better than the SOTA that is available for such tasks. The take-home message for this is PRISM can successfully be adapted to address critical bias. It's a VLM to synthesize high-resolution and high-fidelity language-guided counterfactual images. These images can be used for robust classification and can also be adopted to other modalities. We show that in the paper, so if you're more interested, please refer to the appendix. Just a quick 30-second teaser, PRISM also led to development of a lot of other foundational works, specifically with reinforcement learning, and also talking about disentanglement. So if you're interested, do check them out. They are already accepted to different venues, including MICI. Just one notable point that I would like to bring over here is we are already releasing a model at megapixel scale. So this is the first time a foundation model is able to synthesize image as 1024 cross 1024 and even beyond, which is 2048 cross 2048. And you can look at the resolution of these images. They are pretty high. The paper is still in review. We are still waiting for the result. And that the model, once accepted, will be made public. Finally, I would like to thank all the sponsors who generously donated to contribute to this work being done by us. I would like to thank all of you for your attention. Merci beaucoup. And finally, this is the link to the project website. The poster number is F230. If you're interested, I'll be happy to talk more about it. Thank you.
Thanks for the presentation. The floor is open for questions. Go ahead.
Yeah, thank you very much for your interesting talk. I would just be interested if you have already considered medically pre-trained models. and fine-tuning them? Because I know that Stanford also has this Röntgen model,
Yes.
which is validated and also capable of synthesizing high-fidelity images.
Yeah. So very, very good question. And I'm familiar with Röntgen, the one that deals with X-rays. So one thing that I didn't talk about is the resource deployment behind this. The models that it is being compared to, even Radidit was trained with 8 or 4 800 GPUs running for 380 hours from scratch. Our model uses pre-trained stable diffusion, trained it for 7 hours with half the resource, which is 4 800 GPUs. So in terms of resource deployment, we are very low cost, still powerful enough to do these kind of tasks. Now, coming back to your question, if I take a pre-trained medical foundation model that has already spent sufficient resource in training that model, now even if I fine-tune on top of that, I may or may not improve the performance. So essentially, it's a question of resource. We haven't, though, compared our method of pre-training on top of any other pre-trained medical image, but we show the performance comparison on how those methods, which is what was there in SOTA. So Radidit is trained on, it's a medical foundation model that was given by Microsoft. So those approaches, we do compare it to, but we don't fine-tune.
Okay, thank you. I have one short question.
Yes.
Do you also have the capability to model the severity? I mean, now you can remove the pathology, but can you also modify the severity?
Great question. That was one of the papers that was shown. It was accepted at CVPR workshop. So please do check it out. We model the severity. And we control not only severity, we control different aspects of a given image. So given a start point, we are able to control different trajectories where we talk about the severity of the disease. We talk about a number of devices that are present, changing any other properties in the model, all using language guidance. So we did do that in a separate paper.
Perfect. Thank you very much.
You're welcome.
Thank you for the presentation. I just have a quick question about how you chose the classes that you trained your model on. If I'm not wrong, you trained your model on cardiomegaly, pneumonia, and support devices. Why these three?
It's trained on everything, like all 14. In the paper, it's mentioned in, I guess, first page of appendix. It's trained on everything. We just show some of the results here, but it's capable of taking into account all of them.
Okay, thank you.
Thanks a lot. Let's thank the speaker again. And then we can move on to the last presentation. This one here. And we can
Sorry, I've got it now. Yes, so our last talk for this is sequence models for continuous cell cycle stage prediction from bright field images. Our presenter is Andrea Salati.
Can I take this here? Yeah. All right. Hi, everybody. I'm Andrea Salati. I'm doing my PhD in EPFL, Lausanne. And today I'm going to talk about the cell cycle and how to infer cell cycle phases from videos, basically. So the cell cycle is so important it almost doesn't need an introduction, but here I am. So the cell cycle is divided in 4 main phases, which is G1, S, where we duplicate the DNA, G2, and finally mitosis, which is also subdivided in other phases. It's obviously tightly linked to cell growth, DNA repair, and metabolism. And the dysregulation of the cell cycle drives cancer, and that's why a lot of cancer treatment basically target checkpoints between these phases to slow down the progression. So when it comes to image the cell cycle, I'll talk about 2 main categories of imaging that we can see. One is label-free microscopy, and we have modalities as bright field, dark field, or phase contrast. And you image the cells as they are. They don't need any engineering. And although subtle cell cycle changes, they are usually not very well captured. However, when we actually bring in fluorescent markers, they are really good. Of course, they provide really high signal-to-noise information about the process that you're studying, if you tag the right protein. Of course, they require genetic engineering, but although there's also the risk of photobleaching and phototoxicity. So I will talk a lot about this Fuji system, which is a system made of 2 reporters, fluorescent, which tag 2 proteins. One is CDT1, which is a reporter that marks the exit from mitosis. And the other one in green is geminin, which is a reporter that marks the onset of DNA synthesis. This is a rather old system, but it's still very used. Now it's been upgraded, but it's very common in wet labs. So here we can see a classic sort of Fuji profile where we have these two, the magenta line and the green line, which are the intensity of the 2 reporters. And we can see in the phase transitions are marked between G1 and S and between S and G2. And you can see our data from our lab, and that's basically how our model will see the data. We see the bright field, and this is images of the nuclei because we segmented only the nuclei of the cells, so it was easier to do. And then on the last line, we have the Fuji reporters together. And so the dataset was collected by my lab, and it's composed of RPE cells, which are cells from the retina, which cycle in around 20 or 24 hours. And we have both wild-type cells, but also cells treated with a drug for breast cancer, which is called palbociclib. Cells were imaged for 70 hours, and the resolution is every 5 minutes, so not super high. And we have 4 channels. We have the bright field, we have the Fuji that I talked about, and also we have H2B that we used for cell segmentation. So this is a video. This is a label-free modality. This is phase contrast. And as you can see at the beginning, we don't see a lot of morphological changes but as soon as we hit the M phase, we can see that now there's really drastic morphological changes, and like easily even humans can annotate and can understand what's happening. We see the chromosomes, just to show that it's easier to see even with a naked eye changes in the M phase. So this is to just explain a little bit what the models out there did in the past. So far, all the models, they used a label-free modality, so no fluorescence. For example, the bright field. They labeled only the submitotic phases that we saw in the previous video. While the method they used, fluorescent marker-based, were indeed able to annotate also phases coming from interphase, which means all phases which is non-mitosis. So the question we want to answer is, can we predict the interphase states only for bright field images? And the answer is yes, but with a caveat. We're not doing it only from single frames. Since this experiment, usually they're carried out with time-lapse microscopy, why not use the full track, so the full story of a cell going through the cell cycle? And in order to take advantage of this time sequence structure of the data, we use sequence or temporal encoders, which were developed first to handle sequences like sequence of words in natural language processing. But of course, they can use for sequences of anything. So in this paper, we conducted an ablation study where we compared multiple time encoders. So we have a baseline for a model with no time encoder, which we call the single frame model. Then we have some time encoders which are called causal CNN, which is basically does a convolution over time, but always looking at frames that are in the past rather than the future. Then we tried out this rather new architecture, Mamba, which is sort of a faster alternative to the transformer, which is also causal in this case. And finally, we have the Holy transformer as our last architecture. What does the model do? The model basically takes as input sequences of Fuji intensities, sequences of bright field images belonging to the same cell going through the cell cycle, and predicts basically 2 numbers for each frames, which is the intensities of the 2 fluorescent reporters, green and red. In order to embed the images, we used a ResNet 18, We even tried fancier, I think we tried Dino, the transformers, but it didn't really change much. And then, of course, these embeddings are passed to the sequence encoder. And finally, we trained it with supervised learning because our dataset has also the ground truth. So here are the results. Basically, as we can see, for example, in the image here in the figures, we have the two channels that we are predicting with the two sort of different shapes. In black, we have the ground truth, and we can see that basically the prediction gets better with the complexity of the time encoder. Also, I should mention that all the temporal encoders had the same amount of parameters to sort of carry out a fair comparison. And basically the result is that the transformer beats all other methods hands down, probably due to the non-causality of it. So it can predict, to make a prediction, it can also see frames of future. And then here is I would say rather mutilated section of the result and of the metrics, where we are here. I'm just showing the L1 metric, which is basically just a vertical error compared to the ground truth. Then, in order to test further and go to an out of distribution case, we trained on healthy cells, and then we tested on drug treated cells, and with this drug palbociclib, that basically elongates the cell cycle in general, but specifically it really elongates the G1 phase, as we can see from the box plots. And basically this test also sort of confirms the result that we saw before. The transformer, especially in this case, is able to generalize better to this tracks. They are mainly a lot longer than they are usually. They're in average twice as long, while the other methods showed some strong form of bias, sort of remembering the length of a sequence and rushing to the end, while the transformer, in most cases, of course with a lower performance than before, manages to adapt pretty well. So as conclusions, so we saw the sequence models accurately predict cellular dynamics in control image settings, with non-causal models outperforming other methods. This offers a powerful tool to study proliferation or cancer progression. Of course, we would love to scale to larger data sets with specifically more cell types, because cells look a lot different from each other. And this could enhance the prediction on the drug effects. And it has the potential to free fluorescent channels to then perhaps dedicate it to something else, for example, differentiation genes, and study the interplay of the cell cycle with this other phenomenon. And with those, I think there's a picture of my lab, and thank you for your attention.
Okay, we'll take questions. Looks like we have one coming. Go ahead.
Yeah, thank you. This was a very interesting talk. So we are basically trying to do this in human tissue. So we are staining tissues with CDT1, geminin, and other markers, and trying to deduce cell cycle kinetics in a piece of tissue. So we can actually take the actual tissue from the patient. So I'm wondering if any of your methodology can actually be applied to a static system, because we don't have, obviously we have no reporters, we don't have this very nice longitudinal data, but we have snapshots of the cells in the tissues at different stages of the cell cycle.
I think then this would resort more to the, I guess, the single frame method. So in your case, I'm just wondering, so you have marked already Fuji red, but you would like not to mark it in the best case.
We use CDT1, geminin, and 4 other markers to mark the stage in the cell cycle.
Okay, I see.
We cannot put fluorescent reporters into formalin-fixed tissues.
Yeah, I mean, at least for this cell type, it was very hard to perform it, and with the resolution of our data, it seemed the single frame prediction was extremely noisy. So I think that would be hard, but maybe with high resolution, maybe it could work, but I'm not sure.
Okay, thanks.
Okay, if there's no other questions, let's thank our speaker again. And that concludes the session. Thanks, everybody.
I was just wondering because some people bring a laptop and others don't. So.
Yeah, she had notes.
Okay.
Yeah, it depends. Do you have the PowerPoint?
I have PowerPoint.
Yeah, then you have the normal. Here, I can show you. So then you really have this normal view, also with notes, etc.
Yeah, I like the mirrored version better. But
I think we can also, or you have to ask them, they can do it. But
sure, no, this is also fine.
but you can also just make that bigger, right? And you also have the mirrored
I
version.
think you can move this to the right and then it disappears.
Exactly.
Yeah.
But yeah, some people
get
have
distracted by the notes, and I was removed.
So tonight's welcome reception is actually also a dinner. You don't need to go searching for food. There's going to be plenty of food at the reception. Okay. I heard there were some questions about that, so just wanted to put your mind at ease. All right. Go ahead.
It's really hard to compete with good food claims now. Anyway, welcome to the last session for today. My name is Jannis Hagener from the University Medical Center in Göttingen. And it's my pleasure to host this last session, which is kind of a special session because it's about the MIDL challenges. If you haven't heard about that, following the open science nature of MIDL, of course, we are hosting challenges as well. If you don't know about that, check the MIDL website, the MIDL.io, the general one. There is a description on how to host a challenge and what are the nice benefits of that. And luckily, there is a bunch of challenges that are already ongoing within the MIDL community, and we will have presentations of 2 of them, including first results, as far as I know. So we are very happy and to have the presentation of the first challenge, which is the Monkey Challenge, presented by Dominique van Midden.
Yes, it works. Well, good afternoon, everyone. I'm Dominique van Midden, pathologist and a PhD student from Radboud University in the Netherlands. And it's my pleasure to present you the Monkey Challenge here at MIDL. For me, the first time to attend the MIDL conference. And I will approach it a little bit from a pathologist perspective, because I don't have an AI background, so I depend totally on my team members and also the participants, of course, from the Monkey Challenge for the AI development part. Yeah, an AI grand challenge, or what is a challenge? I think most of you are familiar with challenges or know what a challenge is, but it's a global AI competition where the AI community is encouraged to participate and solve different types of AI tasks. And Monkey was hosted on the Grand Challenge, which is an open science platform that allows medical researchers and data scientists to work together and try to build, validate, and apply AI models. The motivation for the Monkey Challenge is mainly the the kidney transplant patients. We see that the amount of kidney transplants that are done each year are increasing. So we see annually an increase of 2% in Europe. And inside the Netherlands, where I work, we had in 2024 1,000 kidney transplantations that were performed, and also 1,000 patients that are on the waiting list to get a kidney transplantation. And the main priority is after a kidney transplantation to prevent rejection and maintain graft function. So we want the kidney transplant to stay healthy. And that's also where the kidney transplant biopsy comes in, because it's still the gold standard to diagnose the cause of the graft function decline. So we want to see if there is rejection, if there is some kind of infection that is the cause of the graft failure, or even toxic causes of the graft dysfunction. So it doesn't have to be rejection, but we want to know what is the cause, because if you know the cause, then you can treat it. And outside of the diagnosis, you also have prognostic information inside of the biopsy. So if you look at the histology, you can see more active lesions or chronic lesions, and chronic is mainly the scarring. And that gives a little bit of information about the course of the kidney transplant survival. As pathologists, we use the Banff classification system to score the kidney transplant biopsies, and that consists of 17 items. So for each biopsy, we have to assess or score 17 different items. Mainly, it is the different tissue components. So if you look at kidney tissue, you have blood vessels, you have the glomeruli, which are the blood filters, also the tubules, where the urine production is, and you have to look at all these compartments and see if there's inflammation or if there is chronic damage. To make it more complex, these 17 items are subcategorized in 4 subcategories, so no, mild, moderate, and severe. And I depicted here two on the slide. So for active, an example of interstitial inflammation, where you see on the left a normal picture, so no inflammatory cells, and on the right a lot of tiny purple dots, the dark purple dots. So that are the inflammatory cells, and that's severe inflammation. And also a chronic example where there is scarring. And that's important because scarring is irreversible, so treatment won't help or will not return it to normal. So you will remain some kind of graft function decline. You will not return to normal function. Where the active inflammation, if you treat it, you expect it to be able to return to normal. So then you will have a good kidney transplant function again. This is just to illustrate. I won't go into detail on this, but there is, with these 17 items, there is a lot of combinations that you can see in a kidney transplant biopsy. More than 1 billion combinations are possible. Eventually, they all lead to 1 out of the 6 diagnostic categories, so that simplifies it then again. So you end up in one of the 6 final diagnostic categories, which you use for treatment. So I hope that this makes it clear that it is a quite time-consuming and also semi-quantitative and subjective classification system, and then also containing challenging morphologies for the pathologist. So there's quite some inter-observer variation. And we think that AI might be a nice tool, especially because this band classification system is really quantitative and nicely subcategorized, so AI might help. And it's a continuation of previous work, so we have already some segmentation models just to divide the kidney tissue in the different compartments, but it doesn't yet include inflammatory cells, so we can't go towards the band classification system. So that was the main goal, to add the inflammatory cells, and that's why we have the monkey challenge. As the data set, because that's of course important to create an AI model, we collected around 120 slides from 6 international pathology departments. They provided us with their PES stain slide and also their own scan. So, and at our own hospital in Radboud, we scanned it again with 2 different scan profiles. So we have each image in 3 scan profiles. So we have some staining variation and also some scan variation. After scanning, the slides are restained with immunohistochemistry for lymphocytes and monocytes. So we have 2 colors in brown. I don't know if it's clearly visible in this tiny picture, but brown cells are the lymphocytes and the magenta cells are the monocytes. So that allows us to make annotations for both cell types. And then we use this immunohistochemistry to create annotations in regions of interest, and that is also the input for the monkey challenge. So we uploaded all PES slides, the annotations are provided to the participants, also the immunohistochemical slides were provided on the website, and we provided them with a baseline model and a tutorial on how to work with all data and how to submit their models. The main task was to detect inflammatory cells overall, so the lymphocytes and monocytes together without differentiating. But we want to challenge the participants a little bit more and see if they would be able to develop a model that differentiates between lymphocytes and monocytes. But that's a little bit for research purposes. So for the band classification, we don't need to differentiate between the 2 cell types. So that was the main goal in leaderboard 1, just overall inflammatory cell detection. We used the free response operating characteristic as evaluation metric. So there, the sensitivity is plotted against the average false positives per square millimeter of all regions of interest. And for the leaderboard, we looked at the final FRC score, which is the average at 6 pre-selected values. Here an overview of some numbers. So we had around 493 participant requests. For the live leaderboard, there were 135 submissions. And the final test phase, there were 7 teams that went for the final ranking. And this is the final leaderboard. So we had the Tayakong team from the Tissue Image Analytics Center in Warwick, UK, who won. Instasec is a team from Edinburgh, and Aeromatrix is a team from India, which became third. And I think here, yeah, you see that the FRC scores are quite close together. FRC, maybe not that intuitive metric. And as a pathologist, especially, I'm always wanted to see the visual output. And here is a nice example, or at least I was very happy with the visual evaluation. It really resembles what I would expect as a pathologist, or what I would score as inflammatory cells. So the output looked quite nice. Yeah, and to get a little bit more complete understanding, we also looked at different performance metrics like precision recall and F1. And here I only depicted it for the top 3 teams. Overall, you see precision recall around 0.6, 0.7, which seems, yeah, fair to moderate. Yeah, the second leaderboard, where the differentiation between the lymphocytes and monocytes, we had the same 3 teams, a little bit different ranking, because the Instasec had a little bit better FRC score for the monocytes. But overall, I think here the results are not that optimal, or at least I think for diagnostic use, this should be better, if it's possible, because this is a really hard task. I think pathologists, we are not able to differentiate between these 2 cell types in PES stainings without immunohistochemistry. So I think, yeah, maybe it's not fair to ask from an AI model to do it better. And that's also where I struggle sometimes myself. How we have all these kind of AI models, how high needs, or what is good enough? Which performance scores are good enough, especially if you have eventually the clinical application in mind. Is it for this task, for example, we don't know how pathologists score. I think they will score worse, I think. So maybe with these performance metrics or scores, it's already a good model to try out in routine practice, or at least test it. For example, also something that we discuss in our team for this task, it may be more important that the precision is a little bit higher than recall. And recall, you expect more false positives, and I think pathologists struggle to ignore false positives. So I think it's more important that the model, the output are the true positives, and that the pathologist might add the missed ones themselves. I think more as a supportive tool, I would see it at this moment. And that's also something I think for renal pathologists, when they look at transplant biopsies, they don't want to miss anything. So if you see a biopsy where you don't see clear inflammation, you are afraid to miss something, because then the patient should be treated. If you say it's normal, then the patient won't be treated for it. So I think that's a main reason why pathologists would want to use AI, to prevent them from missing something. And if there is a lot of inflammation or alterations, that they want the highest scores to be able to put in their reports. And this is an overview of the top 3 teams regarding the AI approaches. I think there have some similarities and also some differences regarding their approaches. For example, the Taiyakong team had a quite strong unified multi-decoder segmentation approach. I think that might be one of the reasons that they end up first. From the Instasec team, we were quite happy to see that they worked with the immunohistochemistry. So they used the immunohistochemistry slides to make additional annotations. So that's also a nice approach. I think that might be helpful for their results. And the Aeromatrix had a nice architecture type, I would think. So to wrap up, I presented you the monkey challenge. So an AI competition for inflammatory cell detection in PES stained slides. I think it's a quite valuable data set, so we tried to have multiple centers that provided us with the biopsies. also including challenging morphologies. So we have a whole spectrum of morphologies that were included. Immunohistochemistry for the ground truth annotations is really important, I think, for this task. And we saw some satisfactory performance scores for the overall inflammatory cell detection. And I think it's a nice example how a wisdom of a crowd approach can lead to diverse methods for the same task, because every team brings their own background and expertise, so that's nice to see. For us, what is next is that we are trying to integrate the different models. So we have the segmentation models that I showed for the structures, and now we have the inflammatory cell models. And then we are starting to create a reader study, and that's, I can show a brief sneak peek how it looks at the moment. We will also do that via Grand Challenge website, where you can make this reader studies. We will provide the pathologists with the original PES and then also a pane with the output of the model, and pathologists will be able to toggle on and off structures and also inflammatory cells. And then on the left you see the different BANF items that they can score, just to see how the AI works in the hand of pathologists, if it will be beneficial for them to score the BANF lesions. And this work wouldn't have been possible without the help of many people, including the participating centers, but also, of course, the participating teams from the Monkey Challenge. Thanks for your attention, and I'm happy to answer any questions or help out on other topics.
Yeah, thank you very much specifically for giving the perspective of a pathologist within this technical community. Stage is open for questions.
Thanks a lot for this very nice presentation. Are you planning to also build an ensemble of all different models in the hope that the one model maybe has picked up on some correct cases and the other on others?
Yeah, it's a fair point indeed. So thanks for that question. At the moment, we are planning to do the reader study with the top performing team, but I think it's very interesting to see if you can make some kind of combination of the approaches. So we have to dive in it a little bit more. So currently we are at least trying or having to integrate our own models and have to be able to run the model on whole site images. I think that's also something that we have to see for computing, etc. But definitely something that we have to look into to see. And we have close communication with the participating teams, so I think they would also be very helpful or interesting to see how they can combine their approaches.
Yeah. Thanks. Have you also seen differences already in this first evaluation of the different models? I mean, besides just the scores, but that you can cluster or see patterns where the one model works better than the others?
Yeah, not that clearly. So we indeed also looked at the individual cases, the test cases, and looked if there were patterns visible, but we couldn't find it clearly at this moment. No.
Okay, thanks.
No.
Yeah, thank you very much. And in the light of time, I would postpone other discussions to the evening event. Thank you very much again. Very nice insights on this challenge. And we have a second one that will be presented as the final presentation of this short session, which is a first glimpse into the Beyond FA challenge, which will be presented by Bennett Landman.
Thank you very much. Button do I hit to end that slideshow? It doesn't say end show.
I'm not sure.
Okay, let's just try closing it. Closing it worked. Okay. There we go. Thank you so much. I appreciate you closing the session with me and sticking around for our lovely reception with dinner. Thank you, Tolga. Today I'd like to talk about the Beyond FA challenge that Alyssa McMaster is somewhere in this room running, right over there. Thank you very much. She lost her voice, so you get me. So first of all, we're doing a Beyond FA challenge. It is ongoing and is about ready to close this month. So if you'd like to enter a challenge in an urgent manner, see Alyssa on Friday, or you can come up and talk to me. What's the big deal? Well, Alzheimer's disease is a very complex multi-system process, and we finally have opportunities for intervention. Really exciting time to be in AD research. In this specification, getting earlier diagnosis than, hey, the temporal pole atrophies early, sparing age, blah, blah, blah. This is a really lagging indicator. Can we get in earlier? Can we find biomarkers? Can we help guide treatment while there's still time to have intervention to do sort of life-changing ideas? For this, we're running a very large consortium called the Alzheimer's Disease Sequencing Project Phenotype Harmonization Consortium, ADSP-PHC, because the NIH loves acronyms. As part of this, we are bringing together an absolutely huge number of data sets. I think we're up at 100,000 imaging sessions with over 48,000 individual people into one NIH-funded NIGADS archive. For this, we have diffusion and then structural, functional, flare, and all these other modalities that you might care about, but we're talking about diffusion today. Well, in diffusion, there's a lot of things we can do. We take in this imaging, we fit local microstructural modeling, we take that microstructural modeling, we can find tracks. In those tracks, we can group bundles, and bundles we can have activity. We can do lots of things with these simple images. Simple. Okay. Problem is, the world at large is by and large looking at that one little tiny piece of all of these kinds of things you can do with these data. And if our very extended team in the ADSP-PHC is producing all these metrics to go up into the cloud computing to let people dig into, should we be doing something better? Should we take the huge processing pipelines, manual control, physical examination of order 100,000 imaging sessions times how many slices, et cetera? There's a lot of things we're looking at. Could we also do your metric? Could we put you in the big table of all the variability metrics across all these people that we're then farming up for optimal diagnosis, imaging, genetics, et cetera, et cetera? And the answer is yes, we have a team of people looking at all aspects of the reproducibility and harmonization. We're getting these together and we're finding metrics that seem to vary. Ooh, they're not labeled. Why are they not labeled? Because what people are publishing on, this is what Alyssa put together in terms of the types of things, are really just FA, the basic diffusivities, and a little bit of tractography. Could we do something a little bit more? Hence the name Beyond FA. We have an example data set where it's a single gradient strength, single shell, sort of the easiest possible thing, the baseline pre-processing. We say, do whatever you want with these data. What's going to be predictive of Alzheimer's disease? So we give you the pre-processed data. Your Docker can do anything you'd like given grandchallenges.org and produce a feature vector. Now we'd normally say this feature vector should predict Alzheimer's disease, which is great. Do whatever you'd like, we'd like to see. Kurt Schilling is a person I work very closely with, made this slide. Just in very simple modeling of in the microstructure, you could have over 480 plausible models that have been published, which keeps our friends in the ISMRM community very, very busy looking at. You could take those up, start layering tracks, look at specific tracks that you think are all put together. We have demographics for who is involved in Alzheimer's disease. This is a relatively small sample of 600 people. I think I didn't put it on the slide. Sorry, Alyssa, I messed that up. But our training and testing sample are slightly different because we figured we'd throw in a little bit of bias for you. And we have all of these discussions. Great. We want to look at it. Do I animate this in? Here it comes. Whee! There's a reason why we didn't just say predict Alzheimer's disease. On this cohort and in this larger sample, we have a new, relatively understudied biomarker that has been shown to be associated with brain dysfunction. We'd like to know if your secret sauce, that feature vector that you're predicting, actually predicts this previously unpublished set of biomarker. That secret sauce will be released at the end of the challenge August 1st. We got a thumbs up, August 1st. And then we'll have all the code to reproduce that external non-imaging biomarker if anybody else is interested in it. So that's the challenge. We give you the data. We give us a Docker, we produce feature vectors all through grandchallenge.org, so the training data are public, the testing data are secret, and then we run a very simple MLP to let you know that how sensitive is your feature vector. If you want our MLP to be boring, just return one thing. If you want our MLP to be interesting, much as you like in there. The code is all Dockerized, it's engaged. We're at the very end of this timeline, so there's still time. You guys are awesome programmers. I've seen some amazing science today. Adam is sitting back in Nashville, still at his desk, I hope, right? It's only 5:30. He's still there. So we can give him a call, set stuff up. Here's the Docker baseline that we just say will predict FA. I know it's a bit of an ironic thing to have the example of the Beyond FA challenge to be FA, but we like irony. You can test out your code. You can run the Dockers locally. You can show everything. It's great. Worldwide map from grandchallenge.org of who's been registering, and a worldwide map of the people helping out in the challenge to make all of this work in the back end. Thank you to everybody who's up here. Alyssa has the short paper with sort of a technical description. Of course, the goal of a short paper is to take that short paper and convert it into a detailed analysis of the actual results. And on Friday, you get to see, I'm going to call them the alpha level results with Alyssa, and ask us any questions. I think I'm on time. So thank you especially to the NIH and the funding agencies. I have time for questions.
Yeah, thank you very much for this enlightening talk. You are on time, but we are not with the session anyway. If there are short questions, we might sneak them in here. One short question.
Or not. I will not head out, and there's still coffee and cookies. So.
That's what I would propose. I think everybody knows that my question would mainly have been, if we don't know enough about this challenge, who can we ask so that we can get on board? And thanks for answering that, including QR codes to contact the right people. Thank you very much. And with that, I would close the session and put questions to the relevant people to the evening event.
And I'd just like to thank MIDL here and the MIDL board and the organizers for having these challenges have deep peer review. There was a lot of people who looked at the proposal documents and have provided commentary that was incredibly valuable throughout the process. If you're proposing challenges, talk to board members, talk to organizers. We're really working hard to make these a positive experience for everyone, the organizers and the community who ends up using these.
Yeah, thank you for that. And so let's thank everybody who proposes challenges. There are others running as well, including these two, but also others. And for the last words, I think Tolga said that there will be dinner today, so don't eat beforehand. There will be nice dinner. Starting at 6:30, and it starts here in this room, I guess. So prepare for dinner in this room at 6:30.
Thank you. Very nice presentation. I turned it on turbo mode. Did you want the 15-minute version or the 6-minute version?
I was serious.